phenomenon that looked very different before. Now, Einstein did something quite similar, but now for, on the one hand, gravity, like somebody in a box that's doing an experiment and dropping a ball to the ground and interpreting it as gravity. That's mathematically equivalent to the same observer, but now in a rocket that is accelerating away into space. This person, this observer, would see exactly the same things, and so there's a symmetry between these two situations. And if you make that a non-coincidental symmetry, but lift it to the level of a physical law, then you can derive all of general relativity from that. And even in the particle model, the standard model of physics, symmetries play a crucial role. There's all these particles which are organized as representations of certain groups, like U1, SU2, and SU3. And then, of course, there's also, these particles which actually carry the forces, the gauge groups. And we'll talk about gauge groups in a minute. Okay, so a little bit of a background slide on deep convolutional neural networks. I hope most of you know about these, but just to get everybody on the same page. So in a convolutional neural net, we start off with, let's say, an image. It's a whole bunch of pixels sampled on a grid. And then we have a little filter here, which we apply, at every position. We sort of slide it over the input image, and then we sort of filter, therefore, the input image into a filtered feature map. And since we can have many of these filters, we can have a big stack of these feature maps. Then there is a different operation, typically pooling of some sort, which then reduces the size of the representation, because this is actually very large to hold in memory, all these feature maps, because it's n copies basically of your image. So then you sort of subsample them in a particular way. Maybe you'll be only keeping the maximum activation for every sort of 4 pixels, and you sort of reduce the dimensionality. This will also give you a little bit of invariance to small, sort of small transformations of the input. And then again, we filter again, so we create a new set of filters. We filter again, and we create a new set of feature maps here. I didn't mention here, there's also nonlinearities in the middle, which is actually very important. Otherwise, you'll just do a big linear transformation, and that's not very powerful. And then in the end, there's maybe a fully connected neural network that then tries to answer the question, is there a person in the image, or a dog, or something like that. And then the free parameters are these filters here, called kernels sometimes. And you can simply, compute the derivative of the objective at the very end with respect to, one of these parameters in these filters. You can organize these computations by what's called backpropagations, basically the chain rule, and to figure out efficiently what the change in the objective would be if I would change this pixel a little bit. And by this, by stochastic gradient descent, we can just train these networks. So if we show this, so here's our filter. Our filter moves over the slide. It should, of course, go off on the right-hand side, but it's just filtering over this image, and then we get a filtered image. Then we typically do some pooling, and then we do some nonlinearity. So here's the famous ReLU nonlinearity. And then we repeat that process many times. Because there's a couple of really good sort of examples where this has worked out very well. There's many of them, actually. This one was published in Nature in, I think, 2016 or something, where they showed that if you collect 100,000 or so images of sort of skin lesions, and you take basically a pre-trained network from Google that was trained on your vacation pictures and your family pictures, and you fine-tune it a little bit on this task, you can do extremely well in predicting, for instance, if this is a melanoma, yes or no. And sort of here, the blue line is the line that's the algorithm at various operating points, and the red dots here are the actual dermatologists who are sort of trying to do the same task. And you can see that, and this is now very common, that these neural networks actually do better, or at least equally well, as the expert, the human expert. But of course, it's a very, very specialized task, and it's very good at this one very specialized task. So here's another one is pathology. So that these huge pathology slides, and you sort of need to go through them and find the regions where there is possibly malignant tissue. And people train these neural networks again in the same manner, the same algorithm. Actually, this Google-derived algorithm, and again, the algorithm performs better than the pathologist. Okay, so now let's just reinterpret maybe this idea of a convolutional neural network a little bit as a message passing algorithm, because that will make it easier to transition to the graph neural nets. So if we think of so this is a sort of the operation that of a sort of convolution that was sort of embedded in this neural net. And we can think of it as basically the central node here, which is sort of moving here. We're actually sitting here. This one is the central node, receiving messages from all the neighbors, where the value of this particular feature is multiplied by a little matrix W, and sort of added into the pool for the new value of the central node. And of course, even the central node can send a message to itself. And most importantly, these messages, these matrices W can be different for each one of these neighbors. Now, for a graph, this is sort of an interesting sort of generalization of this. For graphs, now the situation looks far more irregular. Now, the number of neighbors is actually different for every node, or potentially different for every node. And also, there isn't a sort of fixed ordering of these nodes. I mean, I can drag this particular node all the way here. And of course, I would drag also all the edges with it. And this could be a completely equivalent way of embedding that graph into 2 dimensions. But now the ordering of the nodes has changed. And so there is no natural ordering of your neighbors. And so how do you produce a neural net that is not going to be fitting to this particular arbitrary order that you chose for the neighbors? And how can you implement something that actually works for any number of neighbors? And the answer to that is surprisingly simple. You just use the same matrix W for each one of the neighbors that is not yourself. So the red matrices W1 are now all the same. So that's sort of saying, like in this particular situation, you have an isotropic kernel. In whichever direction you look at, you will get the same message. And that's of course limited in some way, but still surprisingly powerful in another way. So this is the paper we wrote in 2016, graph CNNs. And here sort of it's like a neural net where sort of you take each node, the node receives messages from the neighbors. Again, these are the same matrices. You do this, you push every node, every result on every node through ReLU, and then you repeat this process again and again. And so you interpret this as a message passing protocol between neighbors. In that sense, it's very efficient, and you'll get sort of an embedding of your input graph sort of at the end of that. And you can write that, in this particular way. So a graph convolution star is basically some matrix, some self matrix times the features of yourself, plus looking at all your neighbors NP, some other but matrix K neighbor, but the same for every neighbor, multiplied by the feature values of your neighbor. You add everything, you add nonlinearities, and you repeat this process. Okay, so then we move to this concept of equivariance. Now, what do we mean by equivariance? So this is to try and get some symmetry into sort of the neural net. So a function x to y, so in this case, that's, let's say, one layer of your neural net, or maybe the input x to the final output of your neural network. And 2 functions, symmetry functions, phi x and phi y, which should have operate on these 2 spaces, x and y, and do some symmetry operation on that space. And we say the function f is equivariant if the following holds. It's basically a commuting diagram. If we first apply f, which is, let's say, our convolution, and then we rotate or translate the image, it should give the same result as if we first rotate the input, right, and then do our convolution. These 2 things should come up with the same result. So in pictures, this looks like, I move my gecko to the right, and then I filter, it should get the same result as if I first filter and then move the filtered gecko. That should give the same result. And why that is useful, we'll of course discuss. So you could ask the first question is why are we not making everything invariant, even in the middle of a neural net, right? If we are interested in the end in an invariant map, because basically we're saying, the prediction of if I have an invariant data set, which means that, a cat is a cat, even if it's upside down, then we could make every layer in the neural net invariant. The problem with that is that you lose all the relative information between the sort of features that you detect in the image. So this will be a perfectly fine representation of a human being, where the relative positions of all the sort of the nose and the eyes and the ears and so are all sort of scrambled up. The output would have an equally high probability on this image as this being a human than if you would have a human, which is the normal picture of a human. And so that's not really what we want. So the reasons for equivariance are, first of all, sharing of parameters. So clearly, when we do a convolutional neural net, we have small filters relative to an MLP, which would be a huge number of parameters. If we have like 1,000,000 pixels in our image, and the second layer also has 1,000,000, so we have 1,000,000 squared parameters to sort of manage. Wherefore, a convolution disk could be, a couple of hundred. Now, also, you should imagine that if you have equivariance, the next layer is it's a lot easier for the next layer to detect patterns of patterns, right? So a neural network is sort of a pattern detector at many layers, the levels of granularity. And sort of we are making the task of the next layer to detect patterns of patterns easier by having this equivariance. Imagine, for instance, that if you have a non-equivariant sort of filter, and you would take a picture of a cat, and then you move the cat, a couple of pixels to the right, and the representation at the next layer will be completely scrambled. Well, if you would do that, the next layer would have a very hard time seeing patterns of patterns. And so the last thing is that this sort of abstraction, this process of abstraction, which in physics is sometimes called renormalization group, it preserves symmetries if you have equivariant neural nets. And sort of this is sort of in the picture here. So if I take faces and I rotate my faces, and so that's sort of your orbit of your symmetry in pixel space. Now, if I do my convolution, I get sort of, let's say, an abstract face, and sort of all these faces map to the abstract sort of picture of a face. And now I rotate my face, that is that I get exactly that picture, the rotated abstract face, from the rotated pixel inputs. So this relationship is kind of very natural, and sort of you say that the abstraction preserves the symmetries of our neural net. Okay, so in deep learning, when do we have symmetries? Where are they useful? Well, if I'm detecting nodules, like maybe cancer in lungs, for instance, if I focus on that nodule, the orientation of the nodule is arbitrary. And so I should get to the same prediction if I rotate the nodule around. Same reasoning holds for melanoma, and same reasoning holds for pathology slides. Now the problem is that under rotations, which is sort of a group that is slightly more sophisticated perhaps than translations, the CNNs are not equivariant. And you can sort of already see this in these very early videos by Jan LeCun. You see here, let's say, an image of a fork. Here you see all the feature maps. And as we translate the picture, we see all the feature maps nicely translate as well. But if you rotate it, then you see, yeah, it looks like things are rotated, but they also change dramatically. And so here we don't have this equivariance property. You can also see it here this is done by Daniel Worrell. So you have sort of a rotating image, and if you stabilize, that image by sort of rotating the camera and then looking at the camera, you see that the non-equivariant net actually changes a lot as you rotate the input, where the equivariant neural net will just stabilize. Okay, so a little bit of math then on how this works. So we have a so we can think of a convolution. Actually, I'm looking at time, and I think I'm running a little bit out of time. So if we take a normal convolution, we can think of it as translating our filter and then taking the inner product with the underlying image. We can do exactly the same for more general group convolutions. So now we have translations and rotations. as our basic operation. So now we have an operator TG, which translates and rotates our filter and then takes the inner product with the image. And then you get a convolution, sort of an output of our convolution, which is now a function of the group, both x position as well as orientation of the transformation. And that's then the group convolution. Now, why does that solve our problem, right? So here you see the group convolution, which we introduced in 2016. Here you see that object in action. So here's the group convolution for the group of 4 orientations. And basically what we do is we not only move the filter, but we also rotate the filter. And then we store the result in a different feature map. Now, why is that equivariant? Well, here we're going to see. So here's the input image. And then, so we have an eye and a mouth detector in all 4 orientations. And you can see here the detector fires at the eyes and the mouth. Now, if I rotate the image, then I'm going to get these firings, right? Because now I need to use the rotated filters, and they are sitting in the second feature map. And also I have sort of rotated the orientation of the detections as well. So now the operation, that the symmetry operation that's happening in our feature space is not only rotating the image, but also cyclically permuting through this stack of feature maps. So these now go to these, and you rotate the underlying image. That's the operation. That's why it's sort of equivariant. So very quickly, let's say you have 3 colors, and now I'm going to rotate the 3 colors. Is this perhaps, how do I make this equivariant? Is this a vector field, or would it be 3 scalar fields? It turns out it's 3 scalar fields because as I rotate, these channels don't mix together. And so I can sort of represent that transformation, basically as a diagonal operator. Now, if I take the derivatives, things are different. If I rotate the derivatives, actually, they do mix together. So in other words, to get the rotated version out of, this, I do need to sort of transform between these 2 copies, but the different color channels don't mix. And then basically the situation looks like this, right? So for this is for a particular pixel, the pixels between the 2 feature maps, these 2 maps actually mix together, but the between these and these channels, things do not sort of mix together. And so in general, for steerable CNNs, we have a representation. We have a bunch of feature maps, which are for every pixel on the grid, we have some features, and we have now some transformation matrix rho, which is a representation of that group, which transforms these features around, right? And and we can stack these sort of different representations or irreducible representations in this case, which do not sort of mix together. And if we do that, we can build these steerable CNNs, which are equivariant. And you can see it in action here. So here we sort of have an input is the image, and we sort of rotate it around. Then you can see that in the hidden layers, the feature maps, things sort of also rotate around and change very nicely. So here's vector fields. And if you then stabilize things, then in fact, things are completely invariant, which is what we need for equivariance. So the next topic that I want to talk about is deep learning on manifolds. And so, for instance, you could imagine that you have sort of a meshed 3D structure, and you want to, in this case, do a matching between, the different points on the structure, or you could maybe want to detect, where is the head and where is the hands, et cetera, et cetera. Or if you think about a drone that's looking in many directions at the same time, you can think of the world being projected onto the surface of, of a sphere around the drone. And then as the drone sort of rotates inside that sort of frame of reference, it will see the world sort of transform on that sphere, and that's also sort of a geometric transformation. So this is related. What I'm going to talk about is interestingly related to general relativity, and of course, in general relativity, people figured out that the gravity sort of bends lights. It sort of changes the geometry of space, and sort of it bends light, sort of geodesics in that space like light. And interestingly, my thesis was about that. So I'm sort of made full circle, going from physics to machine learning, and now back to these kinds of gravity in 2 dimensions. What we see here, the problem that we have to solve for, on a manifold is that in a flat space, if you have your convolutional kernel and you have to sort of share it between 2 points, it doesn't really matter along which path you transport that kernel. You always get the same result. Now on a curved manifold, the problem is that if you move your filter in this direction or you move it along this path, they will now be different. And so now things become path dependent, and that makes things difficult. And so here you see, if you unwrap this picture, you get precisely this phenomenon that a ray that goes in here will come out here, and so it is really like gravity in 2 dimensions in that sense. So the problem is, but people, of course, in physics have solved this problem largely, and the idea is that you cannot, on a manifold in general, define a global set of frames uniquely. So you cannot just say, like in a plane, you can just sort of, north and south, and you can sort of all the directions you can just fixate forever, and that's consistent everywhere. But on a manifold, this is generally not the case. Clearly, on a Möbius strip, if you move around the Möbius strip one time, your axes get mirrored, right? And so there is a parity sort of ambiguity that you cannot simply resolve. So there's and on the sphere, there's a full orientation ambiguity. And the solution is to define equivariant kernels. This basically means that don't actually define your axis in a unique way, just define it in a axis that's local to that point. And if you compare yourself to a neighboring point, you just have to figure out, okay, how do our 2 reference frames sort of relate to each other, and I have to compensate for that fact, as well as when I take vectors and I move them to a particular point, I will have to parallel transport them over this space. Okay, so to illustrate how that works, we did the full sort of continuous limit in a paper called gauge CNNs, but on a mesh, actually things are a little easier and perhaps also more practical. And why am I saying more practical? Actually, this is a collaboration that we're currently in. For instance, this is a meshed surface of an artery, and you may want to, for instance, predict pressure in this artery. Let's say if it's sort of vulnerable for rupturing, for instance, right? And people have sort of looked at these things, and they have used graph neural networks for them. But the problem is with the graph neural net is that that's actually not sensitive to the geometry of the problem. Similarly here for sort of 3D shape analysis, also people have used graph neural nets for that. And as to give you an example of why graph neural nets are not the best solution for this is, now if I have this local geometry of this local geometry, I believe they're different. They're not exactly the same. Yet a graph neural net would treat these 2 situations as completely identical. And so that's something that we can do better. We want to basically come up with kernels which are sensitive to these angles here, and therefore also they shouldn't be isotropic and the same in all directions. Okay, so now let me say a little bit of how this works on a mesh. It's probably a little bit too complicated, but let's focus on this picture here. So if I have a particular sort of meshed object and I want to compute the messages that are coming from these 3 points to the central point, I first have to pick a reference frame for this point. So that's called the tangent plane. So I'm going to pick a tangent plane and a reference frame, which is I'm putting the green dot here, on the x-axis to the right, on the positive x-axis, and that's one reference frame, and I can do my convolution, and then sort of I get this result. Now I just have to make sure that if I would take another reference frame, let's say the red dot as the positive x-axis, and I do my convolution there, I get a different answer in that reference frame. I just need to make sure that I know how to transform between these 2, and that's of course just a rotation. And so maybe surprisingly, that works. So transforming between these 2 if the convolutional kernel satisfies a particular constraint. And this is called the equivariance constraint, and it's linear, so you can quite easily solve it. Because of time, I will probably just skip this, but this tells you that this was the original graph neural net, This is the actual mesh CNN. It looks very similar. There's a self interaction, there's a neighbor interaction, but the big difference is that the neighborhood interaction now actually depends on theta, and it does not have to be isotropic anymore. And there's this object which compensates for the different reference frames at different points, as well as the parallel transport of vectors from one place to the other. Okay, I'm just going to say a few words that these ideas behind symmetries are not necessarily limited to supervised learning. We can also apply them to, for instance, reinforcement learning. And so in this work with these sort of authors, what we looked at is, okay, maybe in some cases there is a symmetry. So let's say this is the pole balancing problem. I need to keep this pole straight. Now in this situation, I need to move my sort of my train here, my little car to the right to keep it in balance. And in this situation, and which is the symmetric one in state space, I need to move it to the left. And so it basically says that if there is a particular transformation in state space, and then I evolve the policy under that transformation, that should be the original policy but transformed, right? In this case, it's basically a permutation or exchange of going from the to the right should be going to the left, sort of exchanged. And so we applied that to reinforcement learning, and that also gets to very interesting results. Okay, before I end, here are two papers that I just want to, I of course, because of time, I couldn't really talk about these two, but I want to sort of point you to them, maybe if you want to read more about this type of work. One is natural graph networks with these authors, and that's a sort of a generalization of graph neural networks. They're still local message passing networks, but there's a much more general kernel that is certainly not isotropic that you can apply. And the second one is SE3 transformers. So as I said, something like that was actually used for the AlphaFold sort of the algorithm that was recently sort of shown to do extremely well. And the idea there is that you have a graph neural net, but now you have one that is equivariant under rotation. So it's a graph neural net like a molecule, but if you then rotate the molecule around, then you have this equivariance in all your feature maps inside your graph neural network nicely represented. And so that you can read. This was presented at NeurIPS, and you can read it here. Okay, so to conclude then, so symmetries are a very important inductive bias to train neural networks more efficiently. They tend to outperform the non-symmetric ones, certainly if if of course the symmetry is present in the data. On manifolds, the same technology applies, but now it's sort of locally, and we call that gauge equivariance. On graphs, we have also very similar sort of types of technologies that we use. In this case, we usually at least need permutation equivariance, but in this recent paper, we combined permutation equivariance with rotational equivariance, which is this next point. And we can even apply these ideas also to reinforcement learning, where there is sort of an equivariance between changes in the input space and the actions that we take. So in all of this work, and actually other work that I'm doing now, which goes more into the direction of quantum mechanics, I have, and my co-authors have been inspired by sort of physics and the beautiful mathematics that often underlies physics, but also is there in its own right, of course. And I think these physics sort of insights can inspire us to build much better neural networks. And there's many other directions that we want to take this, including chaos theory, quantum mechanics, randomization group. And there's already quite a bit of work on randomization group, holography, and sort of all sorts of other directions. And with that, I'll stop there. Thank you.
Thank you, Dr. Welling, for this wonderful talk. So we have time for a couple of questions. So one question from audience is that how do we make the model inductive as opposed to transducive?
Actually, I don't know quite what that means. Inductive versus transducive.
So maybe they are referring to inductive model being trying to make model more generic so that it would work on surprise data sets, whereas transducive, may would mean that making this model work well on training and testing data sets that that model has already observed. So what our
I see.
priorities should be? Yeah.
Right. So interestingly, in fact, the idea of incorporating equivariance makes it more inductive in that sense, right? Because if you want, if the symmetry, it helps with generalization simply because you're fitting many less parameters and you're putting more inductive biases into your problem. And inductive biases help with sort of getting better generalization performance. And so, in general, it's true that deep learning models are sort of they're not great in transferring from one domain to the next. And so my general answer to the question is more in the direction of variational autoencoders and generative models. So in generative models, you can put a lot of your sort of domain knowledge, you can put them in your generative model. And then in VAEs, we know very well how sort of these types of recognition models work together with the generative models. It's called the encoder and the decoder models there, and how they can influence each other. And so I think that that would be the direction I would take it, or we are taking it in a way to get more inductive biases into these models.
Okay. And here is another related question. So first one is, can symmetry be used to reduce size of a neural network? And second question also pertains to number of transformations. Is that it looks like one would need large number of transformations to get a successful prediction while using transformation convolution. Is that correct, or
Yeah, so with the size of the neural network, it's a bit ambivalent what is meant. I mean, if you think about, say, the number of computations or the number of sort of weights you need to do, then clearly adding symmetries will add more feature maps, and therefore, in some sense, it makes the model bigger. But if you count independent degrees of freedom, which is basically how many free parameters do you have, it typically reduces the number of the free parameters. So it's not entirely clear. And in terms of the yeah, the symmetry groups, I agree. So there is a certain disadvantage in these sort of baking in these mathematical representations into these models, which is that um, for every new group that you want to add, you'll need more and more feature maps, and they can grow exponentially large with the dimensions of your groups, unless you do something smarter, which you can. But the other thing is, of course, is that you really need to know the representation theory for these groups, which means also that you may not know it. And so I'm working on, and I'm in favor of trying to learn these symmetries and sort of not actually giving it all the mathematical structure, but giving a sort of a lighter version of what you would expect how these networks behave under some symmetry transformations, and then learning these symmetry transformations themselves. And they could be groups or non-groups or just basically collections of symmetries. But you would want these sort of hidden layers to transform in some kind of nice way if you transform the input in certain ways. And sort of how to precisely do that is not quite clear. The brain seems to be doing it as well. And sort of I think that's a very interesting research question.
so last question, and this is my personal favorite as I work on climate data, is that what is the scalability aspect of manifold learning and graph neural networks when we apply it to Earth systems, which are inherently complex and have significant information, what we encapsulate in form of teleconnections?
Yeah, so I think we have done quite a bit of work in trying to make it much more scalable. So there is work, I'm not sure if it's already published by some of my colleagues, where certainly on a sphere, and actually also our gate CNN paper has already some of that in it, where we make basically the convolution which runs on a sphere, on a meshed sphere, very, very efficient by basically turning it into a convolution on a plane, but with funny boundary conditions. So certainly, if you deal with a sphere like climate modeling, then I think you can make things arbitrarily fast. You just have to work and work at it and to make things better. On the arbitrary manifold, there is a bit of overhead, I think, computationally, but often you can do a lot of the computations sort of before, so offline. So you can just do a lot of pre-computations and then sort of save them in sort of in kernels, and then you can sort of work with those when you're training the system. So I think a lot can be done still to make this more efficient. Of course, also the hardware can be adapted to it. So there's a whole, depending on how important this becomes in the future, I think we can make it very efficient.
So now I will open the floor to panelists. So any question from our panelists?
Hi, Max. This is Animesh here. I just wanted to kind of ask a question related to some of the works that we have been doing for some time, where we try to identify constant structures within a graph. So this is what we call constant communities. So basically, like, no matter what kind of permutation of vertices you give to the algorithm returns a bunch of nodes always together. So this is what we call many of the communities, you see that once you change the ordering of the vertices, the communities changes because of the optimization, the stochasticity going on there. So but then we observe that there are certain structures which, like, no matter what permutation of vertices you give, these structures are, like, constant over time, over different permutations. So I was wondering, like, this whether this idea of equivariance that you presented would be useful, like, in identifying such structures, because, like, finding them algorithmically is a bit difficult. What we do is so far mostly trying empirical methods, like having different permutations, and from there finding out the different community structures, and then we try to find out the overlap across them, and then so it's a compute intensive process. So I was just thinking, like, if ideas from this equivariance model could be adopted to this kind of problem setting, what would be your high level take on this?
Yeah, it feels somewhat related in the sense that it seems you have substructures which are invariant under permutations.
Yes.
And so I guess you detect them by doing lots of permutations and figuring out which parts are invariant. In our work, so in our work, we basically have to explicitly put it in. But I guess you could sort of, I don't know, if you know how to learn things, you could sort of say, well, let's start with an equivariant model, and then see if you can learn, let's say, the type of representation that comes out. And if the representation turns out to become scalar or invariant, then that sort of community, would be one of these invariant substructures. But it would need a lot of development, because typically these permutation groups are global, not local. But I guess we could define them locally. But yeah, I mean, it's distantly related, but it would need a lot of thinking, I think, to sort of connect these two problems.
Okay, thank you very much. Thanks for the wonderful talk.
So Professor Welling, there are so many questions which we may not have time to go through all of them, but sure, we will compile them and send your way. Thanks a lot for this fascinating talk.
Okay. All right. Thank you, Dan.
Thank you. So our next speaker for today is Dr. Ard Lewis. Dr. Ard Lewis is the professor of theoretical physics at the University of Oxford, where he leads an interdisciplinary research group working on the border between theoretical physics and chemistry, applied mathematics, and biology. His work applies theoretical and computational tools from statistical mechanics to study how complex behavior emerges from the interaction of many individual objects. Professor Lewis received his PhD in theoretical physics from Cornell University. Professor Ard Lewis, over to you.
So thank you very much. It's a great honor for me to be here and speak to you today. I just want to check to make sure that you can see my screen okay. Yes?
Yeah, perfect.
Good. Perfect, great. So it's also a great honor for me to speak right after Max Welling. Max and I were actually classmates at the University of Utrecht, and I spent many an hour with him working over problem sets, often copying down his beautiful solutions. So thank you, Max. Good to see you again. What I want to tell you about is some work we've been doing on neural networks fairly recently, which has been largely inspired by our earlier work on evolution and on biophysics. And that's given us a set of tools or ideas that we're going to apply to neural networks. But first, I'm going to point something out to you that physicists will find typically very, very strange. And that thing that we find very strange is that neural networks have so many parameters. There's a beautiful article by Freeman Dyson, one of the great heroes in physics, of a meeting he had with Enrico Fermi, another great hero, where he came with a particular model of particle physics, which had 5 parameters in it. And he was very proud. He actually traveled across country to talk to Fermi about this. And Fermi pointed out that he had too many parameters and quoted his friend John von Neumann, who said, with 4 parameters, I can fit an elephant. With 5, I can make him wiggle his trunk. It turns out, if you look at this paper from about 10 years ago, you can in fact model an elephant with 4 parameters. And if you add 5 parameters, you can make it wiggle its trunk. So the issue, the intuition that we've received, and that is very important for physicists, is that you should always minimize the number of parameters, because if you have too many parameters, you can fit effectively anything. And so that has is a question for us when we looked at neural networks, because neural networks typically have many, many thousands of parameters, hundreds or billions, even billions of parameters, way more parameters than data points. And just to explain that to you again, for those of you, just explain to you something that we teach all of our undergraduates. I have a bunch of dots here, which are data points, and I say fit a function to it. Well, I could fit a polynomial to it, and if I fit a 5-order polynomial, you see this dashed line, it'll fit reasonably well. There's some bias and some variance. If I pick a 20-order polynomial, which has more parameters and data points, I can fit the data perfectly, but I will have these wild oscillations, which almost certainly mean that I am not generalizing well. By contrast, I take here a simple neural network, a fully connected network with a width of 1,000, layer width of 1,000, and 1 to 5 hidden layers. You see all these curves give me almost exactly the same fit. This neural network fits this line incredibly well. And that's surprising because we know that neural networks are extremely expressive. In fact, there are universal approximation theorems that tell you they can approximate effectively any function. So neural network can also reproduce this polynomial. And why does it choose this smooth curve? In other words, what regularizes the neural network? Or what is the inductive bias of neural network that gives you this smooth curve? And when I first saw this or started thinking about it, I was very confused by why neural networks could work at all, because they've got so many more parameters. This argument became quite popular in the field with a recent paper, which has been very influential, by Zhang et al., where they basically show that if you took an image data set, CFAR10, and you just randomized labels, so you put random labels on, you call a dog a cat, etc., you can in fact train a neural network to perfectly learn that data. So it'll give you 0 training error on that data in a relatively small, modest boost of time compared to learning the correct labels. In other words, neural networks are highly expressive. They've got very high VC dimension, etc. They can memorize data. And so another way of putting this question is, why do neural networks not memorize? Why do they learn something about data which allows them to generalize? So being a physicist, we wanted to go at a very simple problem rather than complicated state-of-the-art ones. And so I'll give you a little example of a problem that we've worked on, and I'll motivate it with a little decision table. So this is a doctor decision table for COVID-19. You're coming to your doctor, you're feeling ill. The doctor needs to decide whether they should send you to the hospital or not, given that there are finite resources. So if you have a fever, a cough, you lost your sense of smell, you're older, you've got heart problems, and you're obese and diabetes, okay, you're going to go sent to the hospital. If you have these same symptoms, but you're younger, but you have these comorbidities, this doctor may send you to the hospital as well. Whereas if you have the symptoms, but otherwise you're young and healthy, the doctor may say, sorry, mate, stick it out at home, etc. So this is an example of the kinds of things you might want to teach a neural network. And the question would be, if I take a bunch of good doctors and I give some examples, can I learn the rest of this function? Okay, my examples are a set of answers to these 7 questions. And the way I like to think about this is that what a neural network is really doing is taking inputs and it's applying some kind of function to it. And that function gives you some kind of output. So in this case, the function is take these 7 inputs and then give as an output a 1 or a 0, yes or a no to the answer. So if n questions, there's 2 to the n possible answers to those questions. There are 2 to the 2 to the n possible Boolean functions, right? Because for every one of these sequences, I could have a set of possible answers. I could have a different set of answers. For example, one very silly doctor might just simply send everyone to hospital, for example. That would be a trivial function. So with this simple example, there are nevertheless 3 times 10 to the 38 possible functions. And the question would be, if I give a subset of the answers, can a neural network learn these functions, the function that the true function? And in order to think about this, I'm going to define a very important quantity, which I'll use throughout my talk. We'll call this parameter function map. What this is basically saying is this neural network is a map from inputs to outputs. It's a function generator. And if I randomly pick a set of parameters, what function will I get? That's the map from parameters to functions. That's the parameter function map. So given a certain set of parameters theta, will I get a certain function in the space of all possible functions that this thing can express? Then I can ask questions such as, what happens if I randomly pick parameters? What will the distribution over functions be? And so we did this for the simple Boolean problem with a small neural network. This neural network had a small fully connected network, which is expressive enough to represent everything. And what we see is something rather surprising, which is that the probability of getting a certain function upon random sampling actually drops down the zip-like law as a function of rank. So I rank them by the probability. Or what's also very interesting is I can make a complexity of the function. So a function that's very simple would be, for example, a function where everything is all zeros or all ones, right? So if this is all zeros or all ones, that would be a low complexity function. This is some kind of complicated sequence, that would be a high complexity function. I use a Lempel-Ziv complexity estimator for this. It's a long story that we write about in more detail elsewhere. But the basic thing we show is that the probability of getting a certain function is bounded by this argument, 2 to the minus some parameter times the complexity with some small offset. I'm going to argue later this is a generic property of the world. So you see the most likely function, which has about 10% of the time, are the functions all zeros or all ones, very simple ones. And then other simple functions are all more frequently. And the more complicated the function is, the less frequent it is. I just want to point out to you that the mean probability of functions in this space is 1 over 2 to the 128. So something like 1 times 10 to the minus 39. So these functions are extremely more likely than the mean functions that you find. So this system is not just biased, it's incredibly strongly biased towards functions with low complexity, low descriptional complexity, low Kolmogorov complexity. That's the nice thing about this model. You can explain and understand things quite well. And how does this link to generalization? Well, what we do here is we do a very simple supervised learning. You pick a target function, you train with SGD to 0 training error on half of the input, so half of the answers of the doctor, and then you predict the other answers the doctor would make. And what we see here is the generalization error of a neural network as a function of the complexity of the doctor's answer. So a doctor gives very complex answers, would be a complexity over here. You see the neural network doesn't actually do very well, but on simple answers, the neural network does very well. And the generalization performance basically degrades with the complexity of the target. Now, the interesting thing is the number of functions is extremely large. So even if I give you half of the inputs, there are still 2 to the 64 functions that will fit that with 0 training error. So a random learner will pick a function at random, one of the 2 to 64 functions, and every single time those functions will generalize basically with 0 predictive power. So this neural network is picking something up. It's picking up patterns in the data, and it's doing that very well for simple patterns and not so well for complex patterns, which is exactly what you expect if you have a system which is biased towards low complexity outputs. It's much more, it's got an inductive bias, and so it will do well on simple functions. You can see this here as well, where here we have a simple target. Here, I show you a bunch of independent runs of SGD. So I start with different set of input parameters and run it to convergence. And this is the target complexity. And you see that what the SGD finds is typically solutions that are low complexity, whereas a random learner finds a bunch of high complexity functions. That's for a simple target. If you take a very complex target, then actually the neural network and a random learner basically do the same. They're both unable to predict anything. So neural networks, I'm claiming, have this inbuilt Occam's razor. And since most of the data that we look at in practice is structured in one way or the other, is in fact low complexity, this is a good bias. This is a bias that is necessary for generalization. And we've done a bit more work on this. You can prove mathematically in some cases that this bias that I just showed you more generally holds for neural networks. I'll skip this detail unless you're really interested in these kinds of proofs. They're kind of fun. So why do we see the simplicity bias? And why did I draw this line with this general P of X function there? Well, then I want to take a step back to a kind of physics or computer science inspired idea that I've been working on for the last 5 or 6 years, which is called simplicity bias. And the intuition really comes from this very simple argument. If I have basically a monkey typing on a word processor, I used to say typewriter, but students nowadays don't know what that is. So a word processor where input is output, how likely is a monkey to type something like just the letter pi? Well, what you'll see is that monkey has a probability of 1 over n, which is the number of keys on the keyboard, to the power m, which is the number of digits you want to get correct. And it's actually true for any sequence. So any sequence of length m will have this probability. It's m plus 1 because it's 3.14, right? That's where the plus 1 comes from. But basically, the probability of getting the sequence is equally likely or unlikely as any other sequence of that length. If, in contrast, the monkey is typing into a computer program, say the language C, then there exists short codes which will generate pi. This is, to my knowledge, the shortest code will generate the first 50,000 digits of pi by Dick Winter in Amsterdam, the late Dick Winter. And so it basically will, this is a difficult code to understand, but it will generate the first 50,000 digits of pi. And the monkey has a 1 over n to the power 133 probability of actually typing that, which is much more likely than typing out pi directly. So what this intuition tells us is if we have something which is generating outputs, generating functions, then it is much more likely to generate simple outputs that have short descriptions and long outputs. And this very simple intuition has been formalized in the field of algorithmic information theory. So this is the idea of Kolmogorov-Chaitin complexity, that the complexity of a string is defined by the shortest code on a universal Turing machine that will generate that string. So this one intuitively simple. It's print 0, 1 50 times, and I get this string. Whereas this string, a binary string, to my knowledge, is random. There is no shorter code than simply printing the sequence. Now, there are lots of interesting issues with this linked to the halting problem. You can't formally ever calculate the Kolmogorov complexity in a generic way. It gives also lots of interesting intuitions. For example, the complexity of a set can be much less than the elements of the set. So the set, all numbers 1 to googolplex, has a short description. I just gave it to you, but there are in that set very complex numbers. And I'm going to use that in just a minute. And the idea of Kolmogorov complexity actually was first put forward by an American computer scientist, Ray Solomonoff, who was asking the following question: what if you randomly type into a computer, say a universal Turing machine? For simplicity, we're going to have it just take binary input codes. How likely is it to give a certain output like pi? Well, he said it's going to be the sum over all programs that give you pi. And how likely you get a certain program, we're going to assume that these are a prefix machine, so that you just type the code and it'll recognize it. So it's 1/2 to the power of the length of the code. That's how likely you are to get a particular code that will generate that output like pi. And the shortest code will be the most likely one to appear. And so intuitively, simpler codes are more likely to appear than complex codes. And this idea of what we call algorithmic probability, I think, is a very profound and deep one, and has been understudied in the field of science in general. In fact, Marvin Minsky, not too long ago, said, before he died, said the following in a talk: "It seems to me the most important discovery since Gödel was discovered by Chaitin, Solomonoff, and Kolmogorov of the concept called algorithmic probability. Everybody should learn all about that and spend the rest of their lives working on it. So here's something very interesting. You see already that things that have a low Kolmogorov complexity might be more likely to appear. This idea was formalized in a kind of different but very closely related argument by Leonard Levin, who pointed out that this algorithmic probability was bounded not only from below by Solomonov's bound, but also from above up to what are called order 1 terms, terms that do not depend on the x that you're trying to generate. And intuitively, this tells you simpler things are more likely to appear. Now, you may wonder why you've not all learned this as undergraduates. Well, it's because there's some formal problems with these coding theorems. So many systems that we care about are not universal Turing machines. Kolmogorov complexity is formally incomputable. And these bounds only hold in the limit of asymptotically large outputs. Now, physicists will often look at these kinds of things, and we're used to deriving particular scaling arguments in certain limits and then applying them nevertheless outside of the formal region where they apply. So with some students, I started working on this, and we also were interested in looking at neural networks, at maps that are not universal Turing machines. And we came up with the following argument, which is a proof sketch, is that I can take a simple map, so it's an input-output map, where I can calculate in principle all outputs, so it's a computable map. I can encode these with a kind of standard Shannon-Fano alias code, and this gives me code words, and then I can invert that, and I'll get an upper bound on a conditional complexity. If my map is simple, then this can be turned into an actual Kolmogorov complexity, and we get this probability prediction. So that's for random inputs on a typical simple input-output map, the probability of getting a certain output x is bounded by this 1/2 to the power of the Kolmogorov complexity. A and B are constants that are independent of the output. So they're not constants you can fix once and then that's it. In fact, you can calculate them a priori in certain cases. The only thing you need is that the map has to be simple in one way or the other. And so we applied this to a wide range of systems. I'll just give you one or two examples. This is the one we started with, which is RNA folds into three-dimensional structures. These can be described by secondary structures, which tells you what binds to what. And what we found is if you randomly take RNA sequences and ask yourself what do they fold into, then simple structures like this one are much more likely to appear upon random sampling of sequences than more complex structures than this one. And the same is true here for L systems, which are actually come from Utrecht originally. It's a botanist, Astrid Lindemeyer, who came up with them. They're now widely using computer graphics. They're a little code that makes you make shapes, like plant shapes, for example. And what you show is if you randomly pick the parameters of these maps, then you will much more likely to find simple shapes than complicated shapes. So you can predict this a priori from this bound. And so that's the bound that we basically used for the neural networks. And our argument, since this argument is very general, we'll argue that even more complicated maps than the one we showed you should show the simplicity bias. And here I show simplicity bias in a convolution neural network on CFAR10 on a reduced data set, because we can only do this kind of calculation on a reduced data set. And you see that you get the same log linear probability versus complexity. Here complexity, we use something called critical sample ratio, which is an idea from Bengio's group that allows you effectively, we think, scales as the Kolmogorov complexity. So that's the first part of my talk. I wanted to argue that these parameter function maps should be, as your first null expectation, exponentially biased towards functions that have low Kolmogorov complexity. And that's good because typically we're interested in data that is in one way or the other structured. However, some of you may say, and I think understandably so, isn't it the case that neural networks are not trained by randomly picking parameters? They're trained by stochastic gradient descent on a loss function, running down some kind of gradients. And it's probably the most common view in the field is still that there's some specific property of stochastic gradient descent that gives you this very good generalization performance. Now, I will say that stochastic gradient descent is an extremely good optimizer, but I'm going to argue that it's not the fundamental source of the good generalization that you get to first order in neural networks. And the argument is quite a simple one. It's that if you have this very large difference in the probability of getting certain functions, so we'll call that like a volume, the volume of the parameter space that goes to function 1 is going to be much, much larger than the volume of the parameter goes to function 2, function 3, all of which may fit your data with 0 error. Okay, when you start your SGD at some initial point high up on loss function, you have this kind of basis of attraction, which is a set of initial conditions that will give you this function as your final condition. And that will typically scale with the size of the basins. And in fact, interestingly, although I don't talk about it here, we've done a lot of work in evolutionary theory, which shows this can predict certain outcomes in RNA structures, for example, where again, you're looking at complicated loss functions, fitness functions, and nevertheless, this is the dominant first order description of how likely you are to get a certain function. That's our intuitive arguments. I just want to take a step back and just remind you again what we mean by functions. So functions are basically maps from the inputs to the outputs. And what we're going to do here is we're going to look at coarse-grained functions. So we'll pick a certain training set S and a certain test set E, and we'll simply describe a function, define a function, or represent it as what it does on that particular set. So for, say, binary classification, which is an easy one to think about, you have some set of inputs and some set of outputs, and a function is basically given a certain set of images, what are the labels that you will get on that set of images? That's the function. And that is a coarse-grained description of the function. And then what I can do as well is think a little bit about this in the kind of Bayesian picture. So I've got some prior functions that tells me how likely I am to get a function on random sampling of parameters. Then I want to get this zero training error. So on my training data set, I only allow functions that give me zero error. So that gives me a likelihood. And then the posterior simply follows some Bayes rule. The probability that I get a certain function, given that I've trained on a training set S, is just Bayes rule. And since my likelihood is just the 0, 1 function, it tells me that my posterior is directly proportional to my prior. And this marginal likelihood, which we're going to see again in a few minutes, or evidence, is simply the weighted sum over all functions that fit the training set. But I don't necessarily need that because it's a constant, which once I've set my training set is fixed. So for a fixed training set, my posterior falls from my prior. So posterior is how likely am I to get a particular function upon random sampling of the parameters. And I can also think about a kind of SGD kind of posterior. How likely am I to get a certain function f given that I trained to zero training error on S? And I'm going to compare those two things. And we do this here for MNIST with a fully connected network using MSE loss. And this is a function where the training set is at 10,000 images. The test set is 100 images. So the function is on the 1,000 plus 100. And I'm going to look, they only differ by what they do on the test sets. And so what I have here, each dot is a function. And on the y-axis, the x-axis, I got the probability of getting that function for SGD. So this is a function with one error out of 100. And that's the most likely function. Here's a function with two errors, the second most likely function for SGD. Now on the y-axis, I've used a Gaussian process technique, which basically just picks random initial functions. And I've used that to calculate the probability that I would get that particular function upon random sampling of parameters. And you see that these are remarkably closely correlated. So the probability that I get a particular function with SGD correlates really well with the probability I get it upon random sampling. And to give you a sense of the scale of this agreement, here I have an approximate calculation of the posterior for all generalization errors, from very low generalization error to 100% generalization error. And what you see is the ones that I'm actually calculating here are ones with relatively low generalization error, and they're in basically from that little box. So inside this little box already, SGD and my random sampling agree very well. I can't get these in SGD because the probability of them is 10 to the minus 100, and I'll never see that upon random sampling. And this last one, I show that basically there's also a very strong correlation between complexity and probability here. So this is basically telling me that my SGD is very closely correlating with the parameter function map. So it's telling them how likely am I to get a certain function is given by how likely SGD maps to that. So what am I arguing now? I'm saying, well, why do neural networks generalize at all in the overparameterized regime? Why is Fermi and von Neumann, can they be ignored in this particular case? Well, it's because the parameter function map is highly biased towards simple solutions, and SGD is following that. There's a second kind of question about generalization, and in this paper here, where we look at SGD, we explore this. Given that a neural network generalizes well already, so given that we understand why it generalizes so well, why this inductive bias, exponential inductive bias with simple functions gives good, allows us to escape this problem of having a very large number of poor functions and give you good functions. Can we nevertheless improve on this by changing hyperparameters or all the kinds of things that in practice you need to do? And the answer is, of course, yes. Here's a good example. So here's a CNN with pooling and without pooling, in this case on fashion MNIST. And so I just want to point out one function in this case for the CNN, which is right here, the zero error, the one error function, so which is the best that it does. And what you see is if you add pooling, your error goes down, but also your bias, so your inductive bias towards this lowest error function, both on the y-axis, which is the random sampling, and on the x-axis for SGD increase. And so max pooling is adding some kind of inductive bias to your system. And a little bit like what Professor Welling was pointing out earlier, which is that you can add symmetries that tell you something about you know about your domain specific about your data that can improve your inductive bias. And looking at this function language is one way of measuring that inductive bias. All right. Now I want to explore this question even further, because I've only given you the claim that simplicity bias explains generalization, but I haven't yet shown you, except in a trivial case of a random learner, that it also can go really bad if the bias goes away. And here I know use another very beautiful idea that comes from physics originally, but it's from a combined work from some people at Stanford and at Google, a very beautiful work on an order to chaotic transition in neural networks, particularly not with ReLU activations, but we have tanh activations, the error function activations. And what they find is that as you increase the width of your initial parameters, you go from an ordered phase to a chaotic phase, where your initial conditions diverge, or in the ordered phase, the initial conditions come back to the same, your Laplace exponents are small. So what we've done is we've applied this idea to our simple Boolean system. Actually, Greg Yang at Microsoft showed us how to do this. And what you see for this example of 5 layers is that if I have a narrow width, so if I'm here with this tanh function, then I get the nice simplicity bias. But as I go into the chaotic regime, the simplicity bias goes away. And that's actually something that we expect, because our simplicity bias arguments have difficulty in chaotic regime. So as you get into the chaotic regime, the bias goes away. And that's super interesting, because I can then try different neural networks with different widths from the order of the chaotic regime for these tanh nonlinearities and see what happens to my system. So what I see here is that my probability versus rank drops as I get more and more chaotic. In fact, this is normal one, and this is the more chaotic one. You see my probability of getting low complexity functions goes way down. And then if I do the same thing I did before, is I try to learn functions of different complexity, then here's my extended neural network, which does well on simple functions. And now my slightly more chaotic neural network, which does not have the same simplicity bias, does remarkably less well. It generalizes poorly on the simple data. You can see that in more detail down here. Here I show the blue is the the normal one. This is the chaotic one. On a complex data set, they do relatively similarly. On a simple data set, you see that there's quite a big difference between the chaotic and the non-chaotic functions that are found. And that's gratifying, because this now gives me a handle to tune my inductive bias and to show you what works and doesn't work. And this is also nice, because now I can look at something else which I haven't touched on yet, is the data. Okay, so what happens to data? So here is example of data for a simple, a modest complexity function here. And what I have each of these dots is basically 1 minus the error of a function at that particular complexity. And I randomly pick a whole bunch of functions, and you see that they got differing errors, or 1 minus epsilon. So this is higher error, that's lower error at the top. And what I'm going to do is pick the best functions for each complexity, because that gives me basically the likelihood of getting the error on that likelihood of getting an error of getting something correct is 1 minus epsilon to the power m if I have m examples. And if I look back at my Bayes theorem, right, which is the posterior is the prior times the likelihood over the marginal likelihood, then if I average this over training set, sorry, then I get this 1 minus epsilon to the power m. That's how likely I am to get the training set with 0 for that particular function. And this is very nice. It's very simple. So here I got this 1 minus epsilon to the power m. And here I show what it looks like for a simple function. So this is a function here, you see that as I multiply m, so I try more and more examples, the probability of getting for just getting zero error gets tighter and tighter around the particular target that I'm looking at, which is exactly what training does, right? It makes you get better and better functions, less likely to make random errors. And then what I need is for a full story is also my prior. Okay, so to get my prior calculated, I'm going to do an approximation. I'm going to take not the prior as a function of f, but the prior as a function of the complexity. And here you see a typical prior for a non-chaotic system. And then if I make my system more chaotic, so I get to the more chaotic regime, then what happens is I am no longer biasing towards simple functions, but functions of higher complexity are all equally likely. Because there are many more complex functions, this thing goes way up, as you see right here. And so this is, I think, important because I can now tune both the data and the prior. And so what you see here in this plot is I took this PFK, multiplied it by my error. So I multiplied this by that one. So PFK times 1 minus epsilon to the power f. And then I predict what kind of functions I find for this particular target for a non-chaotic blue network or for a chaotic network 8. You see that, as you expected, the non-chaotic one gives you functions that are close to the target, and the chaotic one gives you complex functions because there are simply many more complex functions than simple functions. Here you see the same argument I just showed you for simple, medium, and complex functions. And here you see the predictions of what functions you're going to find. Top line is this PFK times 1 minus epsilon to the power m. And the bottom is just directly doing SGD on these systems. So the top one, I'm ignoring SGD. The bottom one, I'm using SGD. And you're seeing that my relatively crude approximation works remarkably well. So it's capturing this interplay of bias and data. And the chaos allows me to tune that back and forth. And I'm quite excited about that. I think that's a nice explanation here for this simple system of how bias and the data, the kind of errors you get on the function that your functions make on the data as a function of the size of the training sets, what the interplay is between these two. And physicists like these kind of simple systems, right? Because we understand what's happening, we've got some control over what's going on. Of course, in practice, you guys who actually work in this field would be interested in more complicated systems. And so here I'm looking at another system, classic system MNIST, which is a digit recognition database. And so there, the difficulty is that I can't do those kind of function. I can't do the error of the functions as a function of complexity as I can do for the Boolean system, but I can look at MNIST itself, which is one particular target function. And here I show you for a non-deep network and then for a deeper network. So deeper you get, the earlier you enter the chaotic, deeper you go into the chaotic regime. So I'm going to choose for this 10-layer network, this is non-chaotic. And then if I start making my initial conditions wider, I get into this chaotic regime. You see my generalization error drops as I would predict. I can also look here in these plots, which are quite similar to these plots that I made before for you right here, these scatter plots of error versus complexity of the function that's found. Here I use a critical sample ratio to look at the complexity. Here I use the error. And you see for the normal network, I get this relatively simple functions and a relatively low error. And for this more chaotic network, I get more complicated functions and a larger error. This is for the MNIST. Here I just show you the prior for MNIST. So this is the PFK. So this is the blue one for the non-chaotic, and this is for the chaotic one. And so as you see that the prior has moved towards more complex functions, and that's what you see in the outputs. The outputs are more complex. And of course, as I can also make my MNIST target function more complex by corrupting the data. So as I corrupt the data, you see that I get to very corrupt data. Basically, my chaotic and my non-chaotic neural network start performing in very similar ways because this inductive bias towards simple functions no longer is that important. All right, so I'll skip that. The last thing I want to say in the last, I think I started, I've got another 10 minutes, I think, yeah. So I want to talk to you about using these ideas to derive bounds. I've just written a very long 75-page review paper on generalization bounds, mainly because I wanted my student to explain it to me. And so the very brilliant student Guillermo Valle Perez came up with this classification of different generalization bounds. So bounds are basically ways of trying to bound the generalization error based on some theoretical grounds. Probably the most famous is like VC dimension, right? So you say the error is something like the VC dimension divided by the size of your training sets. Now, any kind, what we argue here is that any kind of algorithmic independent or data independent bounds simply cannot work for neural networks because neural networks are highly expressive. They've got very high capacity, very high VC dimension. They generalize well because of inductive bias. So what we argue in this paper is that if you want to have bounds that explain generalization neural networks, you must explain an interplay between the data and the inductive bias of your network. If you don't put those in, then your bounds won't work. And so perhaps the most popular and important bound in this field is a Pack-Bayes bound by David McAllister. So it's fundamentally a frequentist thing, because bounds are frequentist things, but it's called Pack-Bayes because it has you'll see in a minute why there's some Bayesian kind of aspects to it. And it basically bounds the error on your on the error of so it's hypotheses, the error minus the training error, by a KL divergence between the real probability of getting certain functions and the probability that you're generating by your algorithm. And what we prove in our paper is actually something remarkably simple, but I think important, which is that if you write down bounds of this type, which is what most successful bounds have used in one way or the other, then you can show that if you use a function-based picture to calculate this KL divergence between the true distribution and your own distribution, then this will always be smaller than any kind of bounds you develop based on parameters. I'm pointing this out because in the field, almost all of the bounds are based on parameters. It's very natural to think about neural networks in terms of parameters because that's what you work on when you try to generate a new architecture. But given that neural network generalize extremely well with a wide range of different parameters, it can't be the case that the fundamental answer to why they generalize is in the parameters. It has to be somewhat in the functions. And here we prove that at least if you can do this, if you can make a bound like this in terms of functions, it will always outperform any kind of parameter-based bound. And so actually we do make a bound of that nature. We call this the marginal likelihood Pack-Bayes bound. And for a realizable case, this is our bound on the error for a certain hypothesis, is bounded by the dominant term is this log of 1 over P of C, where P of C is just the marginal likelihood that I showed you before. It's a sum over all hypotheses or all functions that are consistent with the training sets multiplied by the probability of getting those functions. And so this is our bound that we've derived. We can calculate this marginal likelihood using Gaussian processes, or approximate it relatively accurately, we think, with Gaussian processes. And here we show you, for example, the performance of a neural network as a function of label corruption on MNIST and so on MNIST C4 and fashion MNIST for a CNN and for an FCN. These dashed lines are what SGD does, and the solid line is what our bound does. You see our bound tracks the error relatively well. It's non-vacuous, and it also more or less follows the data that you get from SGD as a function of label corruption. So that's good. We can explain how generalization varies with label corruption or with complexity of your targets. Here we look at how our bounds compare to a bunch of different neural networks as a function of the training set size, so basically learning curves. Very famously, these learning curves have this kind of very fascinating scaling behavior. The scaling parameter is largely dependent on the data and less on the network. So here you see fully connected network, res nets, dense nets, mobile nets. And for each of them, the top lines are our Pack-Bayes bounds and the bottom lines are our SGD generalization errors as a function of the size of the training set. So we're very happy we're able to reproduce the scaling behavior relatively well, and all of our bounds remain non-vacuous. We can also compare architecture. So here's a very famous example. We're looking at a CNN on 1,000, training on 1,000 images on MNIST, which is another kind of data set, a little bit more complex than MNIST. And what you see here is the orange ones are for average pooling, max pooling, and no pooling for a CNN. So what you see is that these are the errors that you get. It improves as you increase the sophistication of your pooling, And here's our packed baseband, which nicely follows this particular property of the neural networks. And here we look at how the error goes as a number of layers, and we're again able to follow the trend that you see in a real neural network. And then finally here, we're going to compare some different architectures, some more state-of-the-art types of networks, not state-of-the-art sizes of our training sets, but because that's still hard to do with our marginal likelihood calculations. And here you see dense nets clearly work better than res nets and then mobile nets, and we're able to capture that difference with our packed basebands. So this is very interesting, I think, because it tells us that we are able to capture some very key properties of generalization using our bounds. Our bound, by the way, does not include any kind of SGD training details in it. It's basically looking, it's a Bayesian, it's basically based on this marginal likelihood that we calculate. And this tells us the fact that our bounds work so well and capture all these trends also tells me that the first order generalization is not explained by details of SGD. What SGD is a very good optimizer, but it's not the source of generalization. All right, so thank you for your attention. I've covered a bunch of different things. I just want to run through it very quickly. Inspiration from science and its implications for DNN. So this is a simplicity bias argument that we originally derived inspired by evolutionary problems. We claim this tells us that neural network parameter function map is biased towards simplicity. Actually, I didn't talk about this, but we did a bunch of work on evolutionary dynamics. We come up with an idea called the arrival of the frequent, which we think explains when you transport those ideas over to neural networks, why to first order SGD finds functions with probability given by the parameter function map. We exploited an order to chaos transition to play with the bias and connect this with Bayes' rule to understand how generalization changes with bias and the complexity of the data. And then this function-based picture was also used to derive what we think are the best bounds in the literature at the moment. And so this really tells us something about neural networks. It tells us that if we want to understand them, we need to understand what their inductive biases are. And if we want to improve neural networks, we need to obviously go beyond just this intrinsic null model of simplicity bias. You want to include something else. So you saw that example with pooling. Pooling changed the bias from the kind of 0th order null model. And I think that any other way we can improve inductive biases will be a key to making them perform better in the future. With that, I want to thank you very much for your attention.
Thank you, Dr. Lewis, for this wonderful talk and your time. We have a couple of questions. So first question is is there any easy way to estimate simplicity bias of a given network architecture?
Yeah, so the way that we calculate simplicity bias in this case is by, you need to know something about the function that you're generating. So the simplicity bias of a function can be calculated in lots of different ways. And one of the arguments that we make in our papers is that although you can't calculate the Kolmogorov complexity exactly, you can bound it in different ways. And as long as your bound is capturing something of description complexity, it should work reasonably well. Then the question is one neural network more simplicity biased than the other? And the argument I think that we have is that's not true unless you start playing with the chaos, which is a way of breaking that simplicity bias. But fundamentally, why does a CNN with pooling do better on images than a fully connected network or a CNN without pooling? That's because you've included some properties that you expect to be true of images in there, and therefore you have increased the inductive bias towards those particular functions. So I think what you really should be asking when you have a particular neural network is not what is its simplicity bias, because they're all simplicity biased in the same way, but what are the higher order biases that have been induced, and are these good for the kind of data that you're trying to treat?
Before I open the floor to panelists, there is one more question from the audience, that what about the effects of implicit generalization of stochastic gradient descent that helps in generalization of neural nets, and how does it fit within your findings?
Yeah, so as I said in my talk, it's very common in the literature for people to say that there is implicit regularization given by stochastic gradient descent. And perhaps there is some. I don't know if there is. I'm arguing something which will be seen, I think, as heretical to these people, but I'm pretty firmly arguing it, which is that in every example I gave you here, stochastic gradient descent is not the regularizer. It's the parameter function map which is regularizing. Stochastic gradients can have small effects. And if you look at our SGD Bayes paper, we look at, for example, classic examples like changing the batch size or the learning rates. And you can see that that has small effects on the functions. Okay. But the first order, the question is, why does this thing generalize given that it's highly expressive? The SGD is not the answer. And so although it's repeated continuously in the literature in a kind of, as if it's some kind of magic mantra, I think it's effectively a kind of magic thinking. And I think I've just shown pretty conclusively that SGD is not the first order cause of generalization. It can very well be the second order cause, which you can just simply see by changing your hyperparameters, right? You change your, I gave the example of batch size and learning rates, and we show in our paper exactly what this does. And that's one way of sometimes improving your generalization, sometimes make it worse. I think what SGD does in practice, or how it walks along the landscape and why it might go slightly towards one function versus the other, is a much more complicated thing. The other, maybe underlying this, is a lot of arguments in literature about flatness. Okay, so the argument is SGD biases towards flatness, and there are even, there's entropy SGD or certain types of SGD methods that are actually designed to increase flatness. And what I would say is that what I've been telling you about the posterior and the large posterior is giving you good generalization, it can be mapped onto flatness. Flatness is like a local measure of this volume, and so there's something there. But what we've got a paper right now, we're looking at flatness in more detail, and I don't think flatness is always a local measure, and there's lots of symmetries in a neural network you can exploit to make your flatness be whatever you want to, even though your volume stays constant. So the point is basically that these arguments about flatness have merit. I think arguments that say that fundamentally it's some kind of implicit regularization by stochastic gradient descent, I do not think those arguments are correct. I recognize that the very, very controversial thing to say, but I think the data is pretty conclusive.
Okay, so maybe we can open the floor to panelists. Any question from our panelists?
Okay, hi, Professor Lewis, this is Anirban. Thanks for the great talk. I was just wondering, and perhaps I've not just understood the path-based bound, the generalization bound that you're talking about. I mean, what I thought, based on the bias, based on the inductive bias issue that you're talking about, what I thought that you were going to generalize the path-based bound by saying that now my generalization error bound is going to have a term that is going to talk about that is going to be dependent on how complex the particular function is, the particular task is. Okay. So is that what your bound really is, or perhaps I didn't? Yeah.
Yes. No. So actually, if you look in the original McAllister paper, he talks about what he calls a preliminary bound, which is just really a generalization of the old pack argument to non-uniform bounds, and that you could use that as would be like a preliminary way of thinking about this. But by using the marginal likelihood, I'll just remind you, is the sum over all functions that are consistent with the training sets multiplied by their probability. So what this is really telling you is, if the probability of your functions that give you zero training error on the training set is large, right? Not just one function, but all functions, right? So you sum over all functions that your neural network generates. If your neural network, in other words, generates functions that give you zero error with high probability, right? Then your marginal likelihood is going to be large. And so if you have, so the point is, the really important point is simplicity bias is just an intrinsic property of the network. It can be bad if your data is complex, right? So what this marginal likelihood is picking up the interaction between the implicit bias that you have, which is a bias towards simple functions, and the fact that this bias is a good bias on the particular data set that you're looking at. And so it's a lot more than just simplicity bias. It's basically including both of those in there. And you can have more primitive bounds, which ignore the data, as it were, and just for a particular hypothesis, like McAllister's. We do this in our paper as well. And you could also show arguments for why that it's not such an interesting bound.
Can I ask
thank you so much.
Yeah.
So Dr. Lewis, thank you. Professor Lewis, thank you very much. I want to correct one thing, which is that when we did exercises together, I was looking at his solutions and not the other way around. But now my actual question. So there is a very clear connection, I think, between this Kolmogorov complexity and Bayes, which is the minimum description length principle. I'm sure you know about it.
Yeah.
There's also a very direct connection between Bayes and stochastic gradient descent, which is stochastic gradient Langevin dynamics, which is basically a noisy version of stochastic gradient. And so it seems to me there's a pretty direct link between, on the one hand, complexity of your function, and on the other hand, basically doing SGD, noisy versions of SGD, which look a lot like stochastic or Bayesian posterior sampling. And so in light of these things, how do you reconcile, in some sense, that with your
Thank you very much. So I think because I've seen some of your work on the Langevin dynamics, and I know about the MDL, which is actually, if you look at the early flatness papers, this is more for the audience. Max, you know this probably much better than I do. They often describe these things in terms of minimum description length. So I'm working on that connection at the moment. I think there's a problem in terms of reconciling them, because what we would argue is that, so when you do some kind of, you add some noise to stochastic gradient descent. Stochastic gradient descent, you can actually map onto a kind of Langevin equation with a certain type of anisotropic noise. And to first order what all of these things converge to is some kind of Boltzmann distribution. And there's basically, what I'm just saying is the entropic term in that Boltzmann distribution is what dominates what you're going to find. Given that you've got a whole bunch of different functions that all give you zero training error, which one are you going to get? So you're going to get the one with the largest entropy. That's an argument which is much simpler than worrying about exactly what the dynamics are. So what I would say is that this argument holds for SGD and for GD and for other variants of this.
Mm-hmm.
And what I need to do, and I've tried on one or two students, and I need to find a student who will run with this, because as usual, it's the students that actually do all the work, is a student that can work through this dynamical question and make this link more strong. But I think you're right. This is a very important link to make.
Thanks. It was a great talk. Thank you so much, Art.
Thanks, Dr. Lewis, for this wonderful talk. In interest of time, unfortunately, we cannot take more questions, but we will try our best to share your questions with the speaker. Thank you.
Thank you very much.
So with that, we'll move to our next talk on Towards Automatic Math Word Problem Solving by Dr. Chin-Yu Lin. Dr. Lin is a principal research manager of Knowledge Computing Group at Microsoft Research Asia. His research interests are knowledge computing, natural language processing, semantic search, text generation, question answering, and automatic summarization. His team focuses on two main research directions: grounded semantic computing, developing semantic computing framework for real-world applications, and services including automatic acquisitions of world knowledge, machine reading for semantic indexing, automatic understanding of user intents, tables, and problem solving, and automatic test generation from structured data, developing models and algorithms to acquire writing and speaking knowledge automatically from massive data. The goal is to enable rich and context-aware interactive client plus cloud computing applications powered by automatically distilled and curated data. He developed automatic evaluation technologies for summarization, QT, and MT. The Rogue automatic summarization evaluation package has been de facto standard in summarization evaluations. It is the official automatic evaluation package for document understanding conference. Before joining Microsoft, he was a senior research scientist at the Information Sciences Institute of University of Southern California, where he worked in NLP and machine translation groups since 1997. He is the secretary treasurer of SIGDAT, was the program co-chair of ACL 2012, was the program chair of AAAI 2011, AI and Web Special Track, and was program co-chair of NLP-CC 2016. Professor Dr. Chin-Yu Lin, we welcome you to our IndoML 2020.
Okay, thank you. I just want to check that. Do you see my slides?
Yes, we can.
Okay, you can hear me, right? Okay. Thank you for
Absolutely.
the introduction, and I'm very happy to have give this opportunity to introduce some of the work we've done at Microsoft Research Asia related to the math problem, word problem solving. Okay, I just want to give some example why it might be a very simple thing, so it's very hard things, but very simple question like the math problem like this. There are 20 horses and chickens at Old McDonald's farm. Together there are 58 legs. How many horses and how many chickens? So this type of question actually been used in the elementary school math very frequently, right? To teach how student test student how to do math. And from there, you can convert it into some kind of mathematical form. But to do this, there are some process involved. For example, you can see that you have to kind of read the nouns like horse and chicken and make it like some representation of variable, right? And then you have to know that horses has 4 legs, is where it's involved, and chicken has 2 legs. And then you have know this like 20 is a sum, and then maybe 58 also is a sum, right? So then you have sum of product, and you have this kind of algebra concept is there. And then this is what the maze word problem actually basically will have to do. Now this is involved, actually you can see natural language processing. You have to understand the questions, and you have some kind of knowledge, not only their math knowledge, but also common sense knowledge, because in the question, there's no description about how many legs horses or chicken have, right? And then so then once you've done that, you have the equation, you have to know how to compute. So that's the kind of very rote math training. And then the other thing is about generalization. I mean, they didn't talk about any particular horse and chicken. So the human can know, okay, you didn't ask about, I don't have to go ask about, okay, do you ask, is there any kind of horse, as particular horse has 4 legs or 5 legs, right? So you just do it. Right, so this is kind of very simple thing, but the human can do it very quickly. Now, so I'm going to give some introduction of this problem in general, and then the talk of this content is mainly based on the research of researcher actually in my lab, Danqing Huang and Su-Ming Shi. And so I want to go kind of give a heads up about one math problem solving is most likely one kind of one branch of the question answering. Right? You can view this math problem as a question, and then you have to come up with the answer given the questions. And so from the question answering, you can see in the broad view, you have this kind of textual reading comprehension type of questions. And for example, given a piece of text, and then I'm asking the question, what are the name of the 1938 treaty? And then reading these things, and we can say, okay, the answer will be Bald Eagle Protection Act. And so this is one type of kind of textual Q&A, reading comprehension. There's another type of Q&A models that deal with like table and databases. Given a table, I'll ask which company has the highest profit. And then you can come up with a SQL query and then just say, okay, it will be Microsoft. Right? So this is really the data, the source is their database or table. And then the question will just natural language questions. And versus what the math question, you will have in the yard, there were chickens and the horses, there are 100 horses and how many legs are there? And then you ask a question about the head and the how many chicken and how many horses, right? And then this is another type of questions. And so among these things, you can see from the math questions, actually you have to come up with the equations. And the equation, mostly like algebra question, you have these many different kind of language description of problem you can get to give the students. Some of them not even in the real world, it could be a fictional, right? And then once you have that, you can convert to the variable, typically X, Y, Z, or some numbers. And you can see the huge number of the natural language descriptions map into very, very, very little vocabularies into the target space. Okay, so it's kind of many to a lot of many, a lot to a few kind of mapping. So it's very difficult in terms of how you learn this knowledge and map into these very little symbols. Okay, so this involves like you have a word knowledge about the you mentioned the problem. It doesn't explicitly mention in the problem, and also you have to abstract from this natural language description into kind of symbols. Now, there are some more observations. For example, the same math problem can be rendered in different kind of natural languages. For example, there are 7 crayons in the drawer. Mary took 3 crayons out. How many crayons are there now? So you can okay, x equals 7 minus 3. So you can get this, there are 4 crayons. And then so the same thing you can say about shopping, but you can also do it in a science experiment. They are very different, right? But then all the mapping to the same equations, right? So really the challenge is really for a natural language understanding system to really understand those texts and kind of map into these solution equations. So there are very variety questions, very different domains, and there's no constraint in the syntax or vocabulary in the paragraph. And it's not a single paragraph like a typical Q&A. It's really give you a description of a problem, and then you're asking about, there may be one single question asking about their answer, what they're looking for. For example, how many crayons are there now? And how much money did Sally spend? How many more bacteria there are now, right? So these are the questions typically you will ask, but then you have a context, multiple sentences together. Then there are different scenarios like daily life, shopping, science experiments. So this has to be mapped into maybe the same equations. And so as we can see, to do this well, we really need to have some kind of, at least some kind of natural language understanding capabilities, and also some kind of math knowledge to know how kind of their addition, subtraction, multiplication, those kind of math concept. And to do it well, you also need to have some kind of common sense knowledge. For example, how many legs an animal has, and then when we talk about the head, okay, typically one animal has 1 head. There are some very special species, actually in Harry Potter, they have 3 heads. Right? So if you talk about that, then you have to really refer to those kind of entity you talk about. And those kind of beyond their description actually exist in the natural languages. Now, so why we want to solve the math word problem? Because it's a challenge in AI. I mean, it's not a new problem, and actually starting in 1960. Recently, there are revival of this, starting with the Allen Institute for AI, and they also there's a big project in Tokyo, University of Tokyo. They talk about Todai robot. They want to pass the University of Tokyo entrance exam by 2021. And in fact, in about 3 years ago, the system already can beat about 60% of their students actually want to get into the University of Tokyo exams. So in China, there's a A36 program. They want to build a human level intelligence QA system, and also want to pass what we call the Gaokao, their college entrance exams. So the other thing is about the math word problem is, once the problem is there, humans very easily can come up with the answer. We can check the success or failure of systems, right? It's very good intuitive metrics. And like a Todai robot project is kind of also, once you pass the exam, then you know, okay, the machine has some kind of capability, like they can pass their college entrance exam in math or other kind of exams. And for Microsoft and also other company actually introduced this problem, this kind of technology can also help to assist in dialogue system like Cortana, and in search system like Bing, in Office the writing assistants, the query about helping system, and Power BI in terms of like natural language to database query. Now, so I want to give a scope about the problem actually we are going to solve, right? So right now, so the math word problem we talk about doesn't include those kind of geometric geometry problem in the math. We only talk about word problem, doesn't involve any of the graph chart, okay? And so the very simple one will be just math extraction. This kind of problem, the computer solve very well. And then you have the word problem. So something like a man bought four dogs, and each weighing 376 pounds. How much did they all weight? Right. And then there's another very small set of problem like a number word problem. It's a word problem, but it's only talk about related numbers, like only how many digits, 5 consecutive numbers. There's nothing about the dog and how many legs, those kind of things. Okay, it's kind of even smaller and it's easier to solve. Now, so the goal for this talk actually going to give a quick introduction about how we approach to building a math word problem solver. Okay, so given that we have to have a set of data for do the scientific research, we have a collection of data to start with, right? So we have a collection of math word problem, and then a very easy solution will be just once you have collected this problem also with the solutions, you can do a very simple kind of search. Once you find some very similar questions or problem before, you can just replace the numbers in the new problem and put it into a template, right? And then you can compute using the equation you already know the computer result. This is a very simple kind of basic approach. And then the other thing is like you can have some kind of intermediate representation of logic form instead of just direct mapping to the questions to the template and then come up with the answer. You can have some kind of immediate form to represent the problem, and then you use that intermediate representation and then map into the equation and to do the final computations. So the reason I will talk about why we have this kind of intermediate steps in one of the section of the talk. And then so in today's talk, I'm going to cover the creation of the math problem solver, math problem data set, and then talk about the how do we go beyond this kind of simple whole equation template matching approach. And then we'll talk about some approaches about the recently very popular neural-based approach to do the directly from the end-to-end system, from the question problem question to the equation, and then you can solve the problem. And then I'll say, before we do, besides we're doing end-to-end, we can also have some kind of intermediate step to do the intermediate translation into logic form, and then we can generate it to the equations. So these are 4 topics we're going to cover today. So the first is about data preparation. Why this is very important? Because before we actually in 2015, there are a few papers come out actually in 2014 about doing this math word problem solving. And then when that come out, and I list the reference on slides, the problem size actually you can see is roughly about under 2,000, right? And then the problem type are not a lot, about 3 or to 1,000 different type of problems, and the period size is small. Now, and then if you check these papers, and in the report, the performance actually can get to about almost 80% of performance. It means give you the test data. You can, if we go into exam, and presuming the computer go to exam, and the computer get to 79% of correctness. So kind of you get a score about 79. So now the question is, to me, actually, I don't think the problem is so easy to solve, right? So the question I have is, has computer already done a good job on these tasks? But obviously, if you look at the problem size actually in these papers, it's not big enough, right? So even you can solve these 2,000 problem, it doesn't mean you can solve all the math problems, right? Yeah, especially, for example, for the algebra 514, right, data set, they have 514 questions. And then so there are very, those kind of question types are 28 different types versus those Dolphin 1878, you have 1,000 types, right? So given that we really want to know if we have a bigger collection of data that represent more different data type, problem type, and how well the current algorithm they already published can work on this data set, right? So, so this is the summary of what you said, right? So, but then the challenge is that you can find those a lot of math problems online. For example, you go to Yahoo Answers, and you see a lot of desperate elementary student, high school student. They will submit the questions to say, "Hey, anyone can solve these questions," and then there do have some really good Samaritan. They actually go there and answer the question for them, and then they solve their homework problem, right? You can get those kinds of things, but then to collect those kinds of things manually and create a very big data set is very tedious. We try it, and we find out that the most you can do, and then we do it very diligently, you can get about 10 problems per hour per person. So it's very costly if you do it manually to do it. You can do it. And so that's why, maybe also why you see there up to 2015, the only the data set we have only maybe get most 2,000 questions. Okay. So I want to give you some example about, I just mentioned about Yahoo Answer. You go there, you can see that there's a mathematic Q&A forums, right? And then you can see the people are asking the questions. And then when people, this is the post the questions, and then the community user can come there and then give the answers. So this actually is a correct answer, but it doesn't give the how that answer is derived, right? But the second answer actually give the good answer and also give their equations, right? And then the third one doesn't really tell you anything. So this is the problem, right? So you go to community Q&A, not always you can find a, not always, so people will answers, but the answer might not be correct, right? And then some people will give you answer, but didn't give you why that is the answer, how the answer was derived. And then there are some people just go there and have fun, right? They don't give you an answer. So that's why when you do the manual annotations, it's very difficult. You have to go through these kinds and fill out the wrong answer and find a good one. And also, what we want is not just the answer. We also want the equation set. They actually help you to derive the answer from their problems, right? So the challenge is, can we, without doing manually, can we actually identify the correct equation answers automatically from the multiple answer user's answer text? So we can think about, okay, we kind of want to do, can we do this as a question? Can we do automatic annotations? We can reduce the human effort. And once we could do that, then we can actually continually crawl these forums and then actually create a large amount of this math problem data set for the machine to learn from, right? But this is not non-trivial, as I said. I mean, but you can have a very simple algorithm to do it. For example, you just go to their forum and then you say, we find all the last number in the user's answers. And then we take the number actually has most common majority numbers, actually all the user agreed. Now we take this as a correct answer. Using this very simple naive approach, we verify that actually to do that, you can find 75% of their answers are correct. If you take this out, 1,100 questions, you have 74% of them are correct. But then this is not good because for us, we want to do really has a collection of data that have high precision in terms of their equation with the problem and also with their answers. So this is not good enough. So what we do is actually we can what we do is to build an automated crawler to crawl this Yahoo Answer website, the math forums, and then we crawl about 1 million posts, right? Beginning 1 million posts, we actually hand annotated about 6,000 posts. We build a classifier. The first step of the classifier to actually fill out those kind of problems that actually are not elementary school math, and they doesn't relate it to the math, or they have some kind of appropriate contents, right? So after that, we done that, we can filter out, and then we reduce the 1 million posts to about 120K data. And then once we had 120K data, we randomly sample this from the 120K to have about 46K data for manually post-processing. So when we do the multiplication, we are not doing the manually post-processing for 46,000 posts. We sample about 3,000, and then we manually annotate those 3,000. And when we're doing those, we actually can process those. We estimate we can process 80 problems per hour per person. And so this process actually we also use this to build a post-processing program. Actually, you go there to remove the spurious word in the extraction from the Yahoo Answer site, and also extract the question and answers automatically. And then we find out that I can show you later, the classifier and the extractor actually did a good job in automatically extracting those answers in equation pair. And at the end, we found we created about 18,000 K of problem from this 1 million post. And among them, 3,000 of them are actually manually annotated. So how do we do the automatic annotation? So from the Yahoo Answer side, as I said, there are answers pattern you can find. So we can create a set of answers, and we actually annotated about 3,000 manually. So we use these 3,000 annotated data as a training data, and we use this training data to use a pairwise ranker. So we have this for each of the problems, the post, we have this correct answer and versus the wrong answer. And we have this 3,000 annotated data. We train a classifier using this ranking SVN algorithm. And then to rank all the possible 18,000 posts actually we have collected. And then at the end, we only return the result has a high score, as I show here. So after we run the classifier and we can have a score, we can find out the curve here. If the confidence score is above 3, then we can get about 80% of higher than 80%, about 90% accuracy. So we can see that if we choose from using this classification algorithm, we can, if the classification algorithm has a score over 3, we are confident the result of the answer could be correct. By doing that, actually create this Dolphin 18K data. And you can see in this table, this new data set has about 5,000, over 5,800 problem type. Is much more than the previous data set. And the carrier size about two times more than the largest one before. And then if you rerun all the state-of-art algorithms at that time, and it can only achieve the best, about 16.7%. So versus already reported and published result in other menus. This is really to say, okay, actually this is also a common problem in the machine learning community and also NLP communities. We strive to actually beat a score. So we get a data collection and we try to do our best. So someone publish a paper, they achieve 78.3%. And next time I will actually do better. I'll have 82%, and then I'll publish the paper, right? So when you're getting that position, then you say, oh, maybe I'll solve the problems. So, but that gives the community a wrong impression about how close we actually already solve the problem. So this data set actually really tell us, no, there's still a long way to go, right? So about using the best algorithm right now for each particular data set we can find. Running on this new data set, we only get about 16% the best result from all these algorithms we tested. Okay. And then one thing is interesting, right? So all these previous algorithms, they are based on kind of the one I just mentioned briefly about kind of the building, given the problem set they saw before, they build some kind of template of the equation set related to their problem they have. So when you see a new problem, then you just do a retrieval, very simple retrieval about the similarities. You find the most similar problem that you saw before, and then you apply the equation with the problem actually most similar, right? And then so in that case, if you see a lot of the problem you see more frequently occurred, you're supposed to be doing better. Right. So in this case, you can see when I see these two sets, you see the title, the training data source, all linear T6 and all linear without T6. So TC means that the data actually using in the test, in the data set, the problem we see at least 6 times in the data set, right? And then for all linear, no, it doesn't include everything. So you only see once, it's okay. And you can see that when you have the training data set increased, actually their performance increased, right? So without doing anything, right? It's very simple retrieval technique. You can do better once you see more data because you just see the same question before, you can answer it correctly. But this also is true for a lot of students, right? So we before their exam, we go there to see if any of the question actually been used as exam by the professors, right? And then we ask our seniors and we get these things, and then we learn it. And then when the exams come, we say, bingo, I see this question, I know this one, I just write the answer, so it's correct. So this is a very simple approach, right? It achieve good result, but not as great, right? So 15.69%, at least on a new data set. Okay. Now, so a summary for this section. So it's so why this is important to start this research? Because if we don't, as we see, as I show, we just continue using the existing data set without asking about the quality and the configuration data set, then you don't know if the current approach already solved the task they're supposed to solve. And then so that's why we create this data set. And then we evaluate all these existing data algorithms at that time. And then so we find out they didn't do well. They only achieve about 16% accuracy. So about 100 questions, you only have 16 of them correct. And so that's can we solve the worst problem by adding more data? Yes, but then it's not completely. So we need really, you have to really have some kind of knowledge, not just kind of remember all the past question actually professor has done, given as exam before. You have to really have some smart. Okay. So now I want to go to another topic about, as I mentioned, that the typical approach will be just check the old problem you know already, and then find the most similar one, apply the template. And as you know, this is not very robust, because a lot of the time you don't see exactly the same one, and then so then you have a problem about can you apply it or not, right? For example, this equation template, right? So I mentioned about there are two questions on the right-hand side. The sum of two numbers is 10, the difference is 4, and so on and so forth. And you have another question, Alice and Bob, it has 8 apples. And these two questions, a problem, you can also have the similar equation. One is the x plus y equal to 10, x minus y equal to 4. The other one is x plus y equal to 8, and x minus y equal to 3. And then so the template I will kept talking about is you just remove those numbers, replace them with the number variable. So you have x, you become a template x plus y equal to n1, x minus y equal to n2. So this is the templates. So next time when I see a similar questions, problems comes in, I run some kind of retrieval algorithms, and I find the most highly ranked result, and I'll get a template, and then I take the questions. For example, if the question is Alice and Bob, then I will replace the n1 with 8, and then with the n2 with 3. Then I have an equation. Then I run the, and then I can solve the equation and get the answers, right? So now the question is, how can we attempt these templates, right? So they are, when you talk about the whole template, it's easy, right? So whole question, whole template, right? But then when we want to map these numbers, to align this number to the slot, is not so easy, straightforward, because there are two main approach. One is to map this kind of key phrases like the verb, right? So the verb, maybe aid and receive means like additions, and lost and miss, so subtraction. So you're kind of collecting some kind of key phrases for math, and then associate them with some kind of operators, math operators. The other one is the template level, right? So I mentioned about the sparsity of the template. And there are also different ways to map and to compute the similarity, right? So you can map on the lexical level. You can do a little deeper about this kind of dependence tree, or other kind of more sophisticated features. But the mapping is actually, if you map the whole problem into the equations, it's not so robust, and then the data sparsity problem is very challenging. Right. So the one very intuitive idea is actually, can we break these kind of whole templates into small pieces? So this come up with these subtemplate ideas, right? So given the questions, right? So you can observe that when we have a discount of n%, mark down the n minus n1%. So this kind of expression can be associated with this expression like 1 minus n. So n is a percentage. Right, and then you can put this out of the like n1% of something, right? Then you kind of time something together. So you have the 1 minus n1 times n2, right? So this is a tree for the template. The reason we can do this, because the observation here, because we have equation, right? The natural language part is very kind of messy. But then from the equation part, it actually is very clear. And then you can really have a correct tree from the expression. And from the expression, you can also align the number to the problem, their natural language expressions. And then once you do this alignment, then the next thing is you can say, okay, then I'll express the whole noun phrase actually cover the subtree mapping to the corresponding expressions. So to do this, we can actually run some NLP tools. You can run this problem through their dependency parser or some kind of other kind of parser, and then you can align this expression tree with the syntax tree, and then you can extract those phrases, and then you can get these subtemplates, right? So for example, you have this 1 minus n. So 1 minus n, many different ways to get the value is n1, a discount of n1, decrease n1, and n times x, the value is increased n1 times the product of n1 and the number, right? So given that, you can collect a lot of this kind of what called subtemplates, and then create these libraries. Now, what do we use this subtemplate for, right? So you can see there are more examples here, like x over y, the ratio of two numbers. And this is actually very interesting because you can see these kind of small phrases. I do believe when the students see these kind of prepare for exams, they also get this idea about, okay, they have this either ratio of two numbers, they have their divisions, and then the product of something, and then you have these multiplications. And then you also have to remember some kind of math equations or math concept about this geometric concept about the perimeters of the rectangular is actually the width and length of the rectangular times 2. Right? So we can mine this kind of thing from this very from this kind of mapping between the natural language path tree to the math expression path tree. Now, how do we use this, right? So we don't use it directly, actually, just because it's fragment, right? So what we do is actually to increase the better matching of their problem to their to unseen problem, right? So once we get a collection of this, now the template itself became the subtemplate. So we can use this subtemplate as a feature. So when the new test question come in, we now have this corresponding expression in natural language in fragment, and also its corresponding math expressions. So we can score instead of the whole problems into word level, but now we can throw in the kind of phrase level. They have a corresponding masked construct on the other side. So then we can actually have the template ranking using this as a feature in the template ranking side, using the same SVM ranking algorithm, also on the answer equation ranking side, right? So then this will be used this way. Then we can find out that this just show that when the template size increased, that means actually the problem actually occurred in the corpus many times. So in this case, I show you from 1 to 100. You can see we see the effect of when you know more of their, you see more of their similar things before, you get better performance. And as you can see, if you see the same problem 100 times or over, the new problem come in, you can achieve about 64.5% correct, right? But this also says that if you practice enough, then you really can do well in this type of task. Right? So you see more anything. Actually, we can reduce their math problem understanding into this kind of subtemplate matching and use that feature to actually do a better matching between their problem set to their potential equations solutions. Now I'm going to using the remaining times about 10 minutes to talk about their end-to-end generations, right? So previously you will say, oh, okay, you have this kind of once you can use their previous themed questions, problems, and then you apply their known answer solutions. But how about those things you didn't see before, right? And then we solved it a little bit by using this kind of subscription matching. But can we do this actually directly generated from their end-to-end system, given the problem, and we just output their equation sequence? And this is considerable kind of insane before, right? But then this we done in 2018. When that time there's no BERT model, no GPT-3. And then so it's kind of, we tried first time to see, okay, how about sequence model? Can we do that? And so I have really a doubt about that. So let's see. Okay, so the motivation really to want to see, can we really solve the unseen math problem? Because that human do that, right? And then we don't need to, once we can do that, then we have to worry about how many different unknown variables will be there, right? We don't want to, as I said, and in previous work, as I talked about the two, one is they're creating the data set, the other one also about suppressions and sub-expression, and the previous work in terms of template matching, scoring methods. They also need a lot of heavy feature engineering and handcraft roles. And so if we can do end-to-end systems and they also perform well, that would be great, right? So then you don't need to go through this laborious process. So we want to try this kind of sequence neural network model to see how we hold any promising result in this to solving this task. Then we used a very simple sequence model at that time, right? So we based in 2016, that's the data recommendation for neural semantic parsing published by Zhao and Liang in 2016, right? So it's an attention-based sequence model with GRU, right? So the input will be the math problem, the problem setup will be input math word problem sequence in the yard, right? And the output, hopefully you will have this kind of x plus y equal to n1 and x minus y equal to n2, okay? And then suppose this actually is a correct equation, solve this problem, right? And then once you have this equation, you just replace, you do post-processing, replace this number n1 with the number in the equation aligned. So n1 equal 10 and n2 equals 2, and then you have this question and you solve the question. So this is the idea. Now the challenge, after we done this, we find out two problems, right? So observation number one, the sequence model can generate. I mean, like when we see this first time, we say, oh, wow, you really can generate something. How could you do that, right? But it does generate sequences, right? So the one thing we observe is actually you can generate out of their vocabulary, not this number actually is not in the question. For example, there are only three numbers, but they actually generate the fourth number. So it generates an equation like x1, x plus y equal to n1, x plus y equal to n4. So the notation here will be xy will be the variable, n1 will be some numbers, right? So n4, so suppose there are three numbers in the problems, but then the equation generates something n4 as their equation template. So so we can introduce, for solving these, we actually introduce a copy. So we want to make sure there's a number. Once you have number, we want to make sure the number is can be copied to the output. So then when you do the ranking, we want to minimize the loss and want to make sure, encourage the attention actually to pay more attention to their number actually copy over, right? In that case, we can reduce the chance to generate spurious output. The number actually is not in there. The number represented by nx here with the index, not in the original problems. Okay, so this is one of the fix we add into the basic sequence student model. The operation, so then in the final equation, we just add these copy components. So you don't always generate from the vocabulary. You also sometimes pick the one actually from their local numbers, vocabularies. Then the other thing about alignment, right? So when we generate the equation, yeah, it's perfectly good, right? So there's no spurious numbers, but then the order is wrong, right? So instead of, I think there's a table here. One is x plus y, the other one is x minus y, but it doesn't matter. So here it will be x plus y equal to n3 and x minus y equal to n1. But then according to the problem, these two should be swapped, right? So in this case, actually the sequence system doesn't really honor their slot positions, right? So we added some a term here to make sure that actually if the number in the source sequence and then the number in the target sequence actually are the same, we want that to actually pay attention to that. And so they will, in this way, we actually enforce the attention to actually pay attention to the order of their position of their number in the equations. By adding these two, there are also other things we can do, right? So we can actually, because this is math equations, right? So you can execute the math equation and check the result, right? And then we also have the result, right? So because once we mine the Yahoo answers, we'll not only mine the equation, we also mine the answers. So we have answers. So we can use the answers as a way to evaluate the generated equations. So this is one interesting aspect, right? Given that, we also observe that when we do the optimizations, we optimize actually using maximum likelihood. We actually optimize to choose just one, the one with the most likely equations. But in fact, the same different equation can provide the same answer. They're all correct, right? So how can we take advantage of this kind of, it's not only just one correct, we can have a batch of their equation that are all correct, right? So we don't want to just use their maximum likelihood. We want to actually have some kind of credit assignment, which is, okay, at the end of the day, if the equation execute with the answer we know is correct, then we want to say, okay, all these equation has the same answer, has the correct answer, should get credit. So we can introduce we can apply the reinforcement learning here by adding a batch of their collect equation into this optimization process instead of just using maximum likelihood, right? And we use their sequence positive network to evaluate, and the result come back as a reward. If it's correct, then it's positive reward. If it's not, then we actually penalize the sequence solutions.
Now, okay, sir.
Okay.
Just in interest of time, we have 2 more minutes.
Okay. Okay.
Yeah.
Okay. I'll finish this and I'll go to the summary. Okay. Okay. And by doing this, you can see that they're doing well, right? So you can see that by adding the copy alignment, but then also chief in the Dolphin's 18K data set, you can see that actually about 28, over 20% accuracies. But if you remember, I just show you that subtemplate based method actually 34.6%, right? And then with all the data set actually achieve 20 much better than this one. So that means that actually template-based method is better than sequence end-to-end method. But after that, we can actually done the analysis. You can find out among these other generated solved problems, 18% is only solved by the feature-based method, and then 5.5% is only solved by the neural-based method, and then in between about 10% they are overlapped, right? So the idea is actually we can combine both of them, do an ensemble, right? So this is 2 examples about a different question. The first one will be solved by the feature-based method, but second one, we never saw it before in a problem set, but we actually can solve it using a neural-based method. So we can come up with the ensemble methods. We can use the neural result to actually score the template, right? So we say, okay, the template actually I saw also the neural template agreed, this is a good one. Then we can say yes. And then in the answer ranking part, we can also say the result actually execute through the neural answer actually agree with some of their equation actually rank high, right? So then also give say, yes, this is actually agree with neural. Using these 2 extra feature, we can do an ensemble. By doing ensemble, actually, you can see this ensemble system actually does better than the feature-based method. Okay, so for conclusion of these sections will be equation generation-based and template-based actually are complementary. Ensemble the method actually achieve better performance. But sequence-to-sequence model actually doesn't really beat the feature-based method. However, the recent development in GPT-3, XLNet, and BERT, and Turing NLG give you some kind of new hope. Actually, might be we'll be able to do it much better. Okay, in the interest of time, let me skip the last sections, and I just go back to the summary. So the recap: how do we build this math or problem solver? So we have created this set of 18,000 problem set, has about over 5,000 different problem set. right? We introduced how we can decompose the big template into subtemplate, apply that as a feature scorer to build their scoring function, make it improve the system. We also introduced some kind of exploration idea into their end-to-end system sequence. I didn't talk about, has time to talk about, is using the intermediate generation form to actually improve the sequence system method. But I will provide the slide and also the reference. So if you're interested in this, you can actually read the paper. Okay, so so this is a summary of the things I just talked about. We contribute in the Dolphin 18,000 problems that can be downloaded from the web, and then we are now exploring using the similar technique. We want to apply into text to SQL and text to Sparkle, text to quote. Okay. With that, thank you very much.
Thank you, Dr. Lin. So we have a question from a participant that what exactly is the annotation about? Like giving a question and an answer, is that annotation, say right or wrong, or it's the pattern of the question?
So the annotation actually, from the Yahoo answer, we actually extract the problem itself is in natural language form, right? So you get a problem, so that's their problem. And then there's one annotation about a problem kind of pre-processing. And then you have also the equations. The equation, you have to do normalization, right? So you have to do the convert all these user use symbol, or a random symbol with standard symbol like S plus Y. We standardize on that, and then replace the number into N1, N sub 1, N sub 2, those kind of things. And then also with the answer, right? Because we have to have the answer extracted from the text, and then we create a data set into like have the problem plus the equation set, and then the answer of the problem. So this is what we call annotations. Right? Yeah.
Right. Thank you for this wonderful talk, Dr. Lin. In interest of time, we cannot take any more questions, but we will certainly forward the comments and questions from our participants. Thank you.
Okay. Thank you very much. Bye-bye.
So moving to the last talk of evening by Dr. Linquin Wang. So Dr. Linquin Wang is a professor of physics at the University of Western Australia. She obtained her PhD degree in astrophysics from MIT in 2001 and was a postdoc at Caltech and Max Planck Institute for gravitational wave physics in Germany before joining the University of Western Australia in 2007. She is a 2009 Australian Research Council Future Fellow and is currently leading the Gravitational Wave Astronomy Group at the UWA. Her recent research interests include online gravitational wave detection, high performance computing, including machine learning and astrophysics using gravitational wave data. So Dr. Linquin Wen would be talking about potential and challenges of machine learning for gravitational wave theory. Dr. Wen, over to you.
Thank you and good afternoon. Can you see my slides and can you hear me?
Yes, we can hear you and we can see your screen.
Thank you very much. Thank you for the invitation. So today I'm here mainly to give an introduction to the field of gravitational wave discovery using machine learning and hope to attract some of you to work in the field, for instance. And as said, I'm actually work at the University of Western Australia. I'm also a chief investigator at Australian Research Council Centre of Excellence for Gravitational Wave Discovery. That's the AUSGRAV. First, just to show that our group that are working on gravitational wave early warning and also on machine learning at University of Western Australia, mainly lots of young students and postdocs, and you can also see it's international. That's about half of our group. So the outline of my talk is, first, I understand that it's a very general audience. I will give an overview, and I will talk about gravitational wave discovery and early warning, and that's my recent research interest. Then I will talk about machine learning for gravitational wave discoveries, the potentials and challenges, and then I'll give a conclusion. First, what is gravitational wave? So gravitational waves are ripples of space and time curvature, actually, in layman's term. So that's actually predicted by Einstein now about 105 years ago. Theoretically, it's a mathematical discovery. And it's actually caused by violent events such as from acceleration of masses. Now, this is important because this is different from electromagnetic radiation that's caused by acceleration of charged particles. So now we can see these are two different aspects. But what can you see? So space and time curvature sounds very abstract. And what you can really see is actually the change of the length, or if you shine a laser back and forth, that's basically like a change of the laser travel time. So what I show on the upper right, it is showing that if gravitational wave is going in perpendicular to this plane, and you can see it's the space and time, the effect of space and time curvature, this oscillation is like you stretching and squeezing a tire. So one direction is going is stretching, the other direction is actually compressing. So that's what you see. That's why we have this second generation detectors made of laser interferometers. Basically, we are going to measure the fractional change of the arm length on both directions. You can see the real detector picture is at the bottom. You see L-shaped laser interferometer. So you can imagine the laser is shining back and forth in both directions and meet at the sensor. So because gravitational wave is basically changing the laser's traveling time, therefore the phases, what you see at the sensor here is the interference pattern of the lasers. Therefore, we actually measure the change of light intensity. So that's basically the theory. So what we have, if you are a physics student, you probably know microsync interferometer, and that's basically a very large microsync interferometer with 3 to 4 kilometer arm length. So there is a worldwide gravitational wave detector network, and some of you probably know already. There are 2 in the US that's called LIGO. One is at Livingston, that's South Coast. One is at Hanford, Washington State. That's at Washington West Coast. So these 2 are about 3,000 kilometers apart. That means the light travel time is about 10 milliseconds, and they have arm length about 4 kilometers. Yeah, and another one is at Virgo, that's near Pisa actually, in Italy, and it's on the arm length is 3 kilometers. And in Japan, there's underground, actually in the mountain, to be more precise, detector that's actually operational now, just at lower sensitivity. It just recently joined the 3rd science round with the LIGO and Virgo. And you'll probably all know that there's going to be a LIGO India. That's basically a copy of LIGO will be sent to India. Therefore, 4 kilometer arm length, and at 2025, it's supposed to operate. So why do we care? Why so many detectors? Because one very important thing is that for localization, we want to know where the gravitational wave is from, because we also don't want to see not only where it is from, what it is associated with, like host galaxies, right? And we also want to see the light, the electromagnetic radiation from there. But all these are conventional telescope, electromagnetic radiation, EM telescopes, they need to know where to point. They usually cannot see the whole sky. Some of them can, but at less sensitivity, there's a trade-off. And therefore, they want to know where to look. But one gravitational wave detector is not very good at telling you the sky directions of a gravitational wave event. We need multiple detectors. What you do is like similar to GPS. What you do is that when you say you have two detectors, the wave far apart, and the gravitational wave front will arrive at one detector first and second later. You measure the time delay. From that time delay, you sort of get the direction, a ring in the sky saying it can come from that direction, but it's a big ring, right? So you need another one to have another ring in the sky. You measure time delay again. That's called triangulation, very common in astronomy. And you get interception of the two rings. You got two sky directions, but each detector also have a little bit directional sensitivity that basically tells you the amplitude is slightly different. So you use that amplitude information to get a sky direction. And this is really important for what I'm going to talk about gravitational wave early warning, because we won't follow up observations from optical telescope, from radio telescope, X-rays, everything. Yeah. So therefore, LIGO India, not only it will help, increasing signal to noise ratio, it will also help the localizations. And so this is basically a paper from I got about the LIGO India. Are you encouraged to ask questions, or you ask afterwards?
So they can ask questions. Yeah, we are enabling questions in Q&A box. So if any question come, I will forward it your way, the way you prefer. Yeah, no, I usually encourage people to ask questions, so I'm just checking. So it is a very exciting time for gravitational wave discovery. Many of you might have heard from the news that 2015, we have the first detection of gravitational waves from the merger of two black holes. It's about, each black hole is about 30 times the mass of the sun. The other one is about 35. They merge into each other. What you see on the left-hand side is x-axis is time. You can see the signal is quite short. It's like a fraction of seconds. Y-axis is frequency, and you can see that's a signal from two detectors. You can see the power. You can see this excess power. It's like a tripping signal. That means the intensity is going up and frequency is going up, just like a chip. And here they also show the waveform, the string, where I show the dimensionless gravitational wave string. It's basically oscillating and then merge and then raining down. And that shows two detectors event. And if you want to listen to it, that's basically a tripping signal. I play it twice. So far, all detected gravitational waves are from the so-called compact binary coalescence, basically either two neutron stars smash into each other, or one neutron star going to a black hole, or two black holes going into each other. The frequency band is about 15 to 2000 hertz because it's ground-based. It's limited by seismic noise and by laser radiation noise and short noise, etc., and also thermal noise. Because of this discovery, 2017 Nobel Prize in Physics was given to three pioneers in the field. One is from MIT, two from Caltech. In 2017, it's even more exciting for us, is the first detection of gravitational waves and the light. Here I just call the light, it's basically electromagnetic radiation. It comes from the merger of two neutron stars. Now you see why they are coming from the two neutron stars. Remember, the electromagnetic radiation come from the acceleration of charged particles. So you need to have normal matter carry charges, and neutron star is one of the, because it contains lots of neutrons and protons, electrons, of course, and therefore the system containing neutron star is very important to generate light for standard physics. Of course, there are also models for two black holes smashing into each other with magnetic field, that sort of thing, but it's a bit non-standard, I would say, not as popular as just normal neutron star.
Just starting from last year, 2019, that will be the starting from April 1st, 2019, ended this March 2020. It was LIGO Virgo collaboration's third science run. And for this one in particular, we started so-called open public alerts. That means every time we detect a signal, we send it to the public as soon as possible. So you basically, there's a website you can see. And the next science run, that means science run means when the data detector is stable, we can actually make measurement, make detection. It's going to start 1.5 years from now, that is in 2022. And it's going to be more sensitive, and we should expect more discoveries. So for last run, we already, for about 11 months, we have 56, 10 months actually, 10 months, we have a break in the middle. We have 56 public alerts sent to the world so that the other telescope can go and follow it up. And here is the schedule. You can see LIGO has 3 science runs. The first one got the first detection. Second one run for 6 months. We got the binary neutron star merger. Third one, it's showing here, we got 56 public alerts. Fourth one is coming in 1.5 years. And about 2025, that should be, we reached the final design sensitivity, and LIGO India is supposed to join at that time as well. So that's going to be very exciting. And for the third science run, you actually can go to this website to see all the public alerts. And our pipeline called SPEAR, developed and run at the UWA, is one of the 5 pipelines that are authorized to submit this open public alert here. So if you can go to that website, you can see this event ID. Basically, S means super event. It's like Superman, but super event. S, year, month, and date. So 2020, March 16, that's the last one. And then they tell you the composition, cannot source. It's in the mass gap. We call it, for the solar individual mass of between 3 to 5 solar masses, we call it mass gap. Below that, we consider it as a neutron star. Above that, it's a black hole. So for instance, this one, it'll tell you there's one component is between 3 to 5 solar masses, because we don't know if it's a neutron star or black hole. And second one tells you the time. Third one, basically GCN, that's like a telegram to astronomers. And then sky direction, as I said, astronomers need to know where to point their telescope, and the sky direction is very important. And then this one is FAR is false alarm rate. That basically tells you the significance of this event. If all these are noise, what is the chance to see a signal like this? So in this case, this signal will have 1 in about 446 years time to see such signal produced by noise. So that's basically the information we want to send it to the astronomers. And we are actually, our group is part of it. We actually have to log in on Caltech. Actually, detector data will be sent to Caltech in seconds. We actually run automated pipeline at Caltech with designated about a few hundred nodes there. So here is the what we have discovered. So you can see that x-axis is time, y-axis is cumulative events. You can see O1 you only get 3 and O2 you get 8. That O means, I think, science run. I don't know why it's called O2 is proper operation, but just O1 means first science run, O2 second science run. And the half of the third science run, we call it O3A, we already have 50, about 50, in total 50 detections, adding O1 and O2. And 26 out of 33 public alert we sent were confirmed. That means we actually have 7 of them get dismissed. And our pipeline detect about 24 out of 26 of them. And there's additional 13 events because data are cleaner now. When we do online, you just have whatever you have, right? You don't know, you have some conditioning on the data, but not clean data. Now you can do a very clean, do some glitch removal, that sort of thing. So you can do better sensitivity so that adding 13 to it. So a total of 39 events were added from O3A catalog. This is also public. Just to show you the waveform, the kind of signal we are looking for, right? And it's basically sinusoid in a short time, but the amplitude is increasing and frequency is increasing with time, chirping signal. And the larger the mass, the shorter the signal, the smaller, lower the frequency, it will merge. That's basically the kind of signal we are looking for. And at this time, we do two things because we know that we are looking for, we actually know exactly what to look for. We just have a very large parameter space to search for. So we actually use so-called matched filtering. That means you cross-correlate the signal with the data. And the second thing is that method is so-called time frequency excess power. You basically do Fourier transform with time. That's what how the first one was detected and look for excess power. That one do not assume waveform. And our group is working on the one with matched filtering. So what we have found for O3, I'm just trying to explain the observables that we want machine learning to help us with. One is total mass in this x-axis, and y-axis is the mass ratio. Q is like smaller mass divided by the larger mass because it's a binary, like two neutron star, black holes, they in spiral and merge into each other. And you can see we already in the left-hand side, mass less than 3 solar masses. We get one more binary neutron star, we get the 2 neutron star black holes, and we get lots of binary black holes. And these are short signals. You can also see that individual mass are very poorly determined. That's bad because we want to know, astronomers want to know as soon as possible, is there going to be a neutron star, right? So that there's more likely, more chance to see light, but actually individual mass is not so well determined. Total mass is not so well determined either, but better than individual ones. At the best determined mass actually is so-called trip mass. It's a combination of two masses. Right. So now I'm going to talk about early warning and multi-messenger astronomy. So the question is, can machine learning help? Of course, the answer is yes. And this is my main research interest, and I think it's also a very important goal for LIGO-Virgo collaboration. So here, I just want to play a short video as a summarize of what we have seen. This is actually the only source we actually, like, for sure detect the light and gravitational wave together in the year in the year 2017, in August 17th. So I just want to play a very short video to summarize what has been found.
For the first time, astronomers have detected a single cosmic cataclysm in both gravitational waves, ripples in space-time itself, and electromagnetic waves, what we typically call light. This hugely collaborative effort includes the LIGO and Virgo gravitational wave observatories, along with a multitude of telescopes in space and on Earth that, together, collectively monitor the full spectrum of light. The spectacular event was produced by the collision and merger of 2 neutron stars. These objects are the burnt-out remains of giant stars that have exploded as supernovae. They leave behind cores of exotic matter composed primarily of neutrons crushed together under the intense pull of gravity. More mass than our sun is compressed into a sphere that is about the size of a city. Astronomers have long known that neutron stars are found in pairs, orbiting one another. The theory of relativity predicts that the motions of these incredibly massive objects should generate gravitational waves. These waves would drain energy from the orbiting bodies, causing them to slowly spiral together and eventually collide with each other in a spectacular explosion. On August 17, 2017, a gravitational wave, CHIRP, was recorded by the National Science Foundation-funded LIGO observatories. And less than 2 seconds later, a short burst of gamma rays, a high-energy form of light, was detected by NASA's Fermi telescope. Researchers quickly realized these 2 fundamentally different types of waves could have come from a single neutron-star merger. If so, it was critical to identify exactly where this had taken place in the sky, and if the explosion could be seen by other telescopes.
Okay, so I actually, it's a very long video, I cut it short. So basically, it's very important to know where that source is. And you probably can see that there are lights. We have detect all sorts of light from this source in gamma rays, X-rays, etc. So now, why do we care about detecting gravitational wave and light together? As said, gravitational wave is actually a very different kind of wave from electromagnetic radiation. And therefore, it helps. It's like opening a new window to see our universe because we see light. So far, we rely on light and particles as well to understand our universe. Now we have gravitational waves, which come from very different mechanisms and different wavelengths, basically. They will give us different information. Gravitational wave tells us the motion of the mass, basically. Electromagnetic radiation tells us about the charges. And combined together, we should know better about the astrophysical process in far away in the universe. Also, the astrophysics strong gravity is actually not so well understood. So we hopefully, I think we're going to have so much to learn from gravitational waves. Another aspect is that we have not caught electromagnetic radiations at the binary merger. We only got the gamma rays. That the reason is that that's a Fermi detector in the space, right? It's a wide field camera. It just stares at half of the sky all the time. That's why we got it. But for the others, we actually need early warning will be important, especially early warning before the merger, so that the telescope can sort of position itself with staring at a certain part of the sky, waiting for the light to come. And that's one thing we really want to do. And I think this probably will lead to most important discovery for the next science run. Another reason we want to do that also from theoretical point of view, also from numerical simulation, the electromagnetic radiation at the merger is possibly very short, like gamma rays itself only lasts for seconds. And we think it's also very short and decay fast. So if you don't catch it and you don't have a wide field camera that's sensitive enough, you lose it. Yeah. So what we really want is a very reliable, fast detection. You don't want to waste, telescope time and money, basically, standing at the noise, right, at glitches, right? So we want reliable, fast detection. We want to be able to identify signals from detector glitches. And we want to do fast gravitational wave localization. That means we want to know where it is immediately so that we can point our telescope. And we also want to know, is there a neutron star? So now you can see we have detection problem, identification problem. We have localization, which you can translate it into, like parameter or even classification problem, and also the classification if it's a neutron star or black hole, right? So you can already sort of put our machine learning into it. So what machine learning can offer? Sorry?
Dr. There is a question from one of the panelists. It says that the multiple detectors help in triangulation, but yeah, do they also help in identification of events since the noise might be somewhat independent?
Of course, yes. Sorry, I did not. I only see one at Q&A. Did not see the chat. Indeed, I emphasize on direction. Yes. So why do we want multiple detectors? Number one thing is make it more sensitive, right? Because yes, if you only see a signal in one detector, you might not believe it. 2 detectors, you believe it more. 3 or 4, that confidence definitely will get built up. And you get higher signal to noise ratio, indeed. And you can also, you get sky direction. That's one of the most important things. For instance, Virgo for the third science run, it's not as sensitive. It could not detect the first, the binary neutron star event. However, the fact it could not see the event actually tells us it's not from certain sky direction, therefore help localization. So localization is important. Another benefit is that when you have multiple detectors, you have more signals, right? Detecting more signals, but gravitational wave only have 2 polarizations, according to Einstein. That means only got 2 unknowns. If you have 4 detectors, say, or 5, and with 2 unknowns, that means you have redundancy information, right? You can use that to help you to confirm that it's a gravitational wave. We actually wrote some paper about it. And also use it to test Einstein theory, because Einstein said there are only two polarizations, but is it really true, right? That can be, that multiple detector will help there as well. Yeah, did I answer the question?
Thanks.
Yes,
Yeah,
thank
that's
you.
good.
Thank you very
Yes, that's a good question. I sort of try to emphasize on the part I really care about. Okay. Yes. So LIGO, what I'm saying, the LIGO in India is really important. Some of you might not know that was offered first to Australia, the LIGO Australia, but Australian government did not take it. So India got it. That's right. It's still very nice, but we are very disappointed. We are still trying to get a detector for the third generation, and that's a side thing. Okay, for what can machine learning offer? Right, speed. As you know, you need to train the say neural network, and that costs time, but it's fine, right? You just do it offline or just for the past. But for detection, it's fast because it's already trained. The second thing, what I can see is that because we need to, one of the biggest challenge is how do you tell the signal from the noise, right? And you basically need to learn about the noise, because detect noise is somewhat unpredictable and it's non-stationary as well. And hopefully we think machine learning might be smart enough to learn about the behavior of the noise. And that's another hope. But the challenge is that because we are using most of us are using machine learning technique almost like a black box, right? You do the tunings, you change the parameters and see how it works. So reliability could be an issue. How can you be sure it's robust? Yeah, you believe where it comes from, the results. And so therefore it's the confidence statement, because we want to know, is it 90% confidence? That sort of thing. But machine learning, I think, has a little bit weakness in that bit. And what we have found is that many methods tuned and work very well for Gaussian noise might not work for real detector noise. And another thing is that we have found is that using machine learning for detection, it's easier to detect gravitational wave from the merger of two neutron stars, or two black holes, sorry, because the signal is very short. And that means in a very short time and limited frequency, the signal is very strong. It's like a burst. But what we really care is the system with two neutron stars or one neutron star with one black hole. All these have very long signals, much longer signals, like could be tens of seconds to minutes compared to binary black hole or fraction seconds, right? So it's actually for each given segment, it's actually quite faint. So we found that's very difficult. So these are the challenges we are going to have. Let's see. Oh, sorry. And how do I move that? Okay. So for our group, one of our interests is online detection. So we have developed something, the pipeline called SPEAR. We use it for, as I said, it's one of the 5 pipelines in the world for LIGO Virgo collaboration. So 2 are in the US, 2 are in Europe, and 1 in Australia, basically. That's us. We do time domain filtering. Remember, we are basically doing matched filtering, but we don't want to do Fourier transform because to do Fourier transform, you have to wait for the data to accumulate, right? So we don't do that. We actually design something, IR filter. If you are from engineering, you probably know what that is. But basically, it's just take an input and take a past output and linearly combine them. And it's not trivial, so we wrote a few papers about it. But it's a time domain filtering, meaning it has 0 latency for each data point. In theory, we can give out a signal to noise ratio. Okay, that's a statement. But of course, when you implement it, it's not as simple. So the filtering will take 1 second for us. And we actually do coherent candidate selection. That means we combine the signals, align their phase together so that we can enhance the signal to noise ratio. That's one benefit of multiple detector. We actually use GPUs. That's basically graphic processing unit you use for graphic of your computer, but gaming industry make it faster for kids to play games. It became a very cheap, HPC, accelerator for embarrassingly parallel algorithm, basically. And we actually, because we are online, we don't have existing, we have to rely on past data for our background. We do some time shifted background and to estimate the noise. And one figure here shows x-axis is as a signal to noise ratio, y-axis is so-called reduced chi-square, basically to test the consistency of the output with the expectation. And the black one is basically noise and red one is a signal. You can see, then we had to apply something like, at this time, we apply something called KNN. It's almost, some people call it machine learning, kth nearest neighbor, basically to determine if a data points here belong to, more likely belong to the background or to a signal. That's what we are doing currently. And we are already triggering gravitational events seconds after the binary merger. Actually, after data is available, not exactly. Binary was merging millions of years ago, but we can do it basically seconds after we get the data. The data is good enough. But as you can see, machine learning can replace most of it. Yep. So that's our pipeline. Now, I just want to show you how the whole process for our open public alert, right? So we have one of the 5 pipelines here. The red one is us. And we also have 3 other pipeline using the also matched filtering based. And then there's a burst search. That means they don't assume no waveform. And then you can see we are the pipeline who will submit triggers. We are actually seconds after the event is available, and other pipeline can be a bit longer or similar, and they'll send it to the GraceDB is the database, and from there you get the sky map. And the red one, I put the red box there, means that can be replaced with machine learning. And you can also do directional search because they are gamma ray bursts, known events. They might be related to a gravitational wave and fast radio bursts. If you're an astronomer, you know that's another mystery. Lots of radio bursts in the sky. You can look for gravitational coincidence. And then from the database, people also do classification. Is there a neutron star? Is there a black hole? Right? What is the mass parameter? What's the distance? That sort of thing. That can be replaced with machine learning. And data quality, you want to know, is it a signal or is a plane flying by? And detector state and also the classification is there. So all these can be done by machine learning. And you can see eventually after all this process, we have something called GW salary. Basically, we'll send the astronomers telegram called GCN notice. Wait, I've got a question. Let me see. Wait. Do I have another question?
Yeah, there is one question that what algorithm was used to generate the graph? Is that KNN or something else?
So that paragraph one, the x-axis, I think you're asking about the last paragraph, right? This one. Is it the one with red and black color? Yeah. Okay, yeah, so x-axis is the signal to noise ratio, the amplitude. So that is generated from matched filtering. So we have 1 million signal templates. We cross-correlate. Every second data comes in, we cross-correlate the 1 million template with the data and generate the signal to noise ratio. So that comes from red bits. And you can see we only trigger at signal to noise ratio larger than 4, because below that it's mostly noise for any detector. But then how do we get background noise? So we basically know that if there's a signal, for any trigger in one detector, right? If there's a signal, it has to happen within 10 milliseconds at another LIGO signal, because these two, the maximum travel time is 10 milliseconds. So we do 100 times sampling back beyond 10 milliseconds. And we know that's noise for sure. We do exactly the same thing. We generate the black points. But then y-axis is chi-square. I don't know, chi-square is basically your data minus expected signal to noise ratio output, square them, add them together and divided by degree of freedom. It's supposed to be 1. So if it's a pure Gaussian noise, and if you extract the data signal completely, it should be like around 1. So flat line here, but of course the waveform is not exact, so it actually goes up a little bit. And noise will just go up because you have noise minus signal, right? So do I answer your question? So you basically take the output from matched filtering and you get signal to noise ratio, and you take that minus the expected signal to noise ratio output, because you know exactly what you're looking for, right? And you square them and divide by degree of freedom, get reduce chi-square, you get the breakpoint, and you do time shift. Okay, good.
Sure. Yeah.
I think another question. Somehow you have to. Oh, yeah. Why don't I not see the immediately? Oh, okay. I think that's just comments, right? So maybe the panelists will tell me. The chair will tell me.
Yes.
More
all good to go. No more questions.
Okay, good. Thank you. So now I'm going to say that, of course, people have thought about machine learning, right? There are about 20 groups working on it. And there are two very good reviews. One is a paper. Oh, I better hurry up. It's a review article at here. And then there is a website that basically collects a collection of all machine learning for gravitational wave sciences. The success, the most successful one comes from the glitch identification, but that's not my interest, but it helps because you apply machine learning, because we know you see all this kind of time frequency on shape. You can see this noise, especially this one, look just like a chip. And for instance, there's work using two-dimensional CNN network to identify them. I think they are doing a very good job. And another group from India, actually IOCA, I think, they do similar thing. They can characterization and classification of transients and consider these are quite a success. And they are also so-called denoising signal noise subtraction and denoising. And you can see that that's also been done. You can see the paper here. That these are also not my interest. Then there's machine learning. There's also, of course, there's very recent work, just 2020 by our colleagues from Max Planck. They do parameter estimation using Bayes and posterior. Basically, well, these are the parameters for the binary, right? For instance, two masses, two spins, binary inclination, distance, and the sky direction, especially sky direction. And they actually apply it to the first event, the binary black hole event, and it looks very nicely, quite comparable to the real parameter estimation published one. There are also people doing detection, and they are more successful in detecting binary black holes, as I said, because these signals are shorter and more localized in frequency. Therefore, it's easier for machine learning, and they compare to matched filtering, and they say, wow, it's similar. However, these are just some injections. So I have not seen detections of gravitational wave events from real data. And that's the challenge we are going to have. Detecting binary neutron star events, that's the hardest one. And we see at least 2 papers, both coming this year. You can see this field is very hard. I mean, very active, but also very hard. Apparently, they claim they have improved the method, and they can probe down to better false alarm rate of 1 per 2 months. That's actually our threshold for open public alert. But they found machine learning is not yet sufficiently sensitive or efficient to match existing algorithm. That's what we have for using matched filtering. But it can be slightly a few seconds faster. So that's the current state. That, as I said, binary neutron star event is harder because it's for the same signal to noise ratio, it's weaker at every time segment. Yeah, and I just want to have a very fresh through of what we have. You can see all sort of methods have been done for detection, for also burst. That means don't know the waveform. For continuous waves that come from a spinning pulsar, which I did not talk much about. Yeah, and for classification, parameter estimation, related population, you can get these from the review articles. And glitch classification and waveform modeling. So what we are doing is that we actually try to do gravitational wave detection, localization, and classification on detector data. And we want to apply them to our online search. That's what we are doing. But it's very challenging. As you can see, most people do well in Gaussian noise, simulated Gaussian noise. We have not seen very successful examples on many detected events. We have seen 1 or 2 examples on the first detected event, but we have not seen too many. And that's actually a challenge because real data is hard to handle. And these are the 3 students. So I will show one. That's our Chayan, is our first year PhD student. And he actually just published the paper last year after 3 years intern with us. And he used the ANN method. And he basically divide the sky into grids and treat it as classification. And you can predict this binary sky direction and crosses where the real direction is. And he got it on. That's actually for injection on the real injection on Gaussian noise. But then once he applied to data, he found the result doesn't work anymore. Hence, he had to change AM plus denoising autodecoder. And he found it worked very nicely. So the big contour is what he had found. The green one is so-called PE, parameter estimation. And note, parameter estimation actually marginalizes over all parameters to get the localization, and we don't, because we want it to be fast. Therefore, we should not beat this parameter we call PE result. But you can see we enclose nicely on it. And that's the first, that's on real data, real event. And actually he tried on all O2 events, second science run event. And you can see it look well, but there are some little issues still to be sorted, but it's very nicely. So I have never seen such a bulk part on success on the real data. And that's for all the event included. And I think he's going to publish the results soon. In fact, he's giving a talk at his, I think, President University on his result just now at the same time. So in conclusion, I think I'm running out of time, but I'm at conclusion now. It is a very exciting time for gravitational wave detection and for multi-messenger astronomy because we want to see light together. And machine learning should be able to make major contributions, especially for early warning because it's going to be fast. Because you spend more time training, which is you can do it ahead of time. I think the existing success already are there for glitch identification and for binary black hole detection, even though not exactly on real data yet, but at least for a few. And we have shown some success on localization for all the second science run binary black hole events, and we're improving on it. But I think it's a real challenge to apply machine learning on detection and parameter estimation with real detector noise and real signal, and for long and faint signals, which is the most important one, the one that contains neutron stars. And I hope maybe there are other young people and interested people will join in the force. Yeah, thank you. I'm done.
Thanks a lot, Dr. Wen, for this very interesting session. Any question from panelists?
I see a question from Q&A. Okay, is SPEAR able to differentiate between two gravitational signals having almost same amplitude but different phases? Well, I don't quite understand the question. You mean the two signals happening at the same time? Oh, can you hear me? Chetan?
No. Yeah,
I guess I don't understand the question.
Chetan, you're allowed to talk. Can you talk?
Oh, now you can you hear me now? You would like to answer the question, right?
Yeah, can you hear me?
Yeah,
can you hear me?
Can talk.
Yes, Chetan, we can hear you.
Okay,
yeah, so,
the question was, I don't understand the question. What do you mean? Do you mean two signals happening at the same time?
No. It's like, suppose if we have two signals and if we calculate a match, Okay, like having same mass parameter, and if we calculate the match of the two signal, it may be different, right? But if they have the same amplitude, the difference comes because of there's a difference in phase, right? For example, if you have one signal having a non-spinning GW and other may have aligned spin GW, there may be a difference in phases, but not as much in the amplitude. So
Okay, that's a good question, because when we detect gravitational wave, we mainly try to match the phase actually, because that's the most sensitive part. And so when we do matched filtering, we actually try to match the phase directly. So yes, we can. Unless we cannot match one of the constant phase, like initial phase, we can't. We have to marginalize over that. But yes, the amplitude is mainly determined by the chip mass. The phase evolution is also determined by chip mass and spins, as you mentioned. And since we know how to calculate the phase, when we do match filtering, we make sure the phase is best matched. So I think the answer is yes.
Okay, thanks.
Okay, thank you.
So I have a simple question. Hi, Professor Wen. Thanks for the nice talk. My question was that I mean, I can understand the application of ML in the other aspects of this pipeline, but I didn't quite sort of. I mean, in terms of the application in detection itself, let's say in the triggering itself, there. I mean, how do you even have the training data, right? Even because we have so few gravitational wave actual detections, right? So how would I create the training data there?
The training data is that we can use past data. Okay, one thing they do is just train it in the Gaussian noise, simulated noise. And the signal we know because we know how to calculate the signal. We know exactly what we are looking for. The signal is not able, we can do injection. The noise is the problem. So usually when we, for instance, for the next science run, we can use the past science run start training already. And then we can do progressive learning is that we add in more data. When you have new data come in, right, you use that data and do the injections for training.
I see. So
yeah,
the noise, although, yeah, sorry, go ahead, Nilada.
No, I guess like they were telling in the material science domain that they are doing the DFT, but there is not much data. So I think professor is telling in that line that to create signals.
Although I guess you're saying that the noise is non-stationary, I mean, still you have some sense of the distribution by looking at past data. That's what, and possibly you're using that. Okay.
Usually we think it's more or less stationary in about 2 weeks time, but beyond 2 weeks, you have to be very careful.
Okay. Thank you.
Thanks a lot, Professor Wen, for this fascinating session. We organizers are very thankful for your time. And if you don't have any questions, we can thank Professor Wen.
And I guess it is pretty late in the night for you. Yeah.
Oh, it's okay. It's like 9, not 10 o'clock yet. I'm happy to answer questions if you have any. Yeah. Thank you very much for inviting me. I'm very happy. As you can see, 2 of my PhD students are from India. They are outstanding.
Thank you.
Thank you. Are there any other questions?
Not as of now, but if any question comes our way, we will definitely email you, and looking forward.
Okay, thank you very much.
Thank you.
And thanks again for inviting me.
Okay. So we are thankful to all the participants for joining us on day 1 of IndoML, and we look forward to another exciting day tomorrow, and we will start as per schedule published on our website. All the recordings would be made available through our YouTube channel. Thank you and good evening.
Thank you. Bye-bye.
Bye. And thanks, of course, to the speakers and all the volunteers. We look forward to. Thank you. Yeah, bye.